Welcome curious minds and sleepy thinkers. Settle in, find a soft place to land. Tonight we're going to dim the lights of our busy world and turn our gaze upward toward the silent, star-strewn canvas of the cosmos. This is a space for quiet wonder, for soft questions, and for the slow, gentle rhythm of the universe itself. We will tiptoe into the great whispering questions that scientists and poets have asked for centuries. What is this vast, dark sea around us? And what unexpected wonders might it hold patiently, waiting for us to notice them? But don't worry, this isn't a race through a textbook. Think of it more as a quiet drift on a calm sea, where the ideas are like distant constellations, and the only goal is to let your mind float free and unburdened until you find a peaceful place to rest. The universe is a place of grand beginnings and cataclysmic ends. And in the heart of these cosmic dramas, some of the most astonishing objects are born. Imagine for a moment a star, a celestial titan, living a long and glorious life. Burning brightly, its fires held in check by the relentless inward pull of its own gravity. But all stars, no matter how massive, eventually reach their final chapter. They exhaust the nuclear fuel that has sustained them for eons, and the delicate balance between the outward push of fusion and the inward crush of gravity is finally shattered. For the truly massive stars, this finale is a spectacular, earth-shaking event, a supernova explosion. But it is in the quiet aftermath of this cosmic violence that we find something truly remarkable. Let us drift now to the heart of that explosion's remnants, where a neutron star is born. It is the dense, collapsed core of a star, a testament to the universe's ability to create something utterly extreme from its own death. Imagine taking the entire mass of our sun 1,000,000 times, the mass of our humble Earth, and squeezing it down into a sphere no larger than a small city, perhaps just 20 kilometers across. The result is a neutron star, a celestial object so dense that its very nature defies easy comprehension. To give you a sense of this incredible density, if you were to take a single teaspoon of this material and somehow bring it to Earth, it would weigh approximately 10 million tons. It would be heavier than every single person on the planet combined. How can we even begin to imagine such a thing? It's like trying to hold an entire mountain range in the palm of your hand. What makes these stars so bewitchingly strange is the physics that creates them. Their gravity is so powerful, so fierce, that it overcomes the very structure of matter itself. Atoms are crushed, their electron shells shattered. The immense pressure forces protons and electrons to merge together, dissolving their individual identities to form a sea of pure, tightly packed neutrons. This is where the star gets its name, a name that whispers of a place where matter has been unmade and then remade into something else entirely. It is a cosmic alchemy of the most profound kind, a natural laboratory for understanding the limits of what matter can become. But their strangeness does not end with density. Neutron stars are also cosmic spinners, rotating at breathtaking speeds. It's an effect that comes from a simple, elegant principle of physics, the conservation of angular momentum. Think of an ice skater pulling their arms in as they spin. As the skater's mass moves closer to the center, their rotation speeds up dramatically. Now apply that principle to a collapsing star. As its enormous mass collapses into a tiny dense core, its rotation accelerates to an astonishing degree, with some neutron stars spinning hundreds of times every single second. Imagine a city-sized object, heavier than the sun, spinning faster than a blender. Can you feel the dizzying wonder of that? And as they spin, they also possess magnetic fields that are millions of times stronger than anything we have ever experienced on Earth. These fields are so intense that they could in theory tear atoms apart and distort the very fabric of space-time around them. They are nature's own cosmic dynamos, generating power and forces on a scale that humbles our most advanced technology. And what a beautiful surprise it was when we discovered that some of these spinning magnetic stars are also cosmic lighthouses. This is where we meet the pulsars, a special kind of neutron star that emits powerful beams of electromagnetic radiation from their magnetic poles. As the neutron star rotates, if one of these beams happens to sweep across our line of sight, we see a pulse of energy, a flash of light that arrives with an incredible, unwavering regularity. These cosmic beacons serve as precise clocks ticking with a consistency that rivals even our most sophisticated atomic clocks. The discovery of these pulsars was not a planned event, but a beautiful accident, a serendipitous find that shows us how the universe often reveals its deepest secrets when we are simply listening with an open mind. The story of the pulsar's discovery is itself a gentle reminder of the power of curiosity. It was 1967, and a young doctoral student named Jocelyn Bell Burnell, working with her thesis advisor Anthony Hewish, was sifting through radio wave data collected by a large radio telescope they had built. She was not looking for pulsars, she was looking for quasars. But in the quiet hum of the data, she noticed a faint, unusual signal. It was a series of pulses so incredibly precise and so consistently spaced that they first earned the whimsical nickname Little Green Men, half-jokingly suggesting they might be signals from an alien civilization. Of course they were not. They were a gift from the universe, a rapidly spinning neutron star telling us its secret, not with a spoken word, but with a rhythmic electromagnetic beat. This discovery was a testament to the unexpected nature of scientific exploration, a beautiful story of how a curious signal in the data can unveil a universe of wonders, a new class of celestial objects we never knew existed. Now let's drift away from these cosmic clocks and towards something even more enigmatic, something that feels less like a beacon and more like a great silent vortex in the darkness. We will whisper the name now, a name that has come to represent the profound and often counterintuitive realities that govern cosmic phenomena: black holes. They are not holes in the conventional sense, but regions in space where the force of gravity is so overwhelming that nothing, not even light itself, the fastest thing in the universe, can escape its clutches. Their formation is a similar cataclysmic tale. A star far more massive than the ones that form neutron stars exhausts its fuel and undergoes a catastrophic collapse under its own gravity. But this time, the collapse does not stop at the neutron star stage. The core compresses to such an extent that it forms a singularity, a point of infinite density. It is an area in space where the fabric of space-time itself is profoundly warped, so much so that it creates a boundary, a one-way cosmic door, known as the event horizon. Once you cross this horizon, all paths lead inward, and there is no coming back. What truly sets black holes apart is their bizarre and extreme nature, a nature that challenges our very understanding of physics. Their immense gravity warps the space-time around them to such a degree that it bends the paths of light itself, a phenomenon known as gravitational lensing. Imagine the black hole as a great invisible lens in the sky, distorting and magnifying the light of the stars behind it. But even more mind-bending is their effect on time. Einstein's theory of general relativity tells us that time itself slows down in a powerful gravitational field. Near the event horizon of a black hole, this effect is so profound that time for an outside observer would seem to stop completely for anyone or anything falling in. This is a concept that tests the very limits of our imagination, a notion that time itself is not an unyielding river, but a fluid that can be slowed or stretched by gravity. It's an idea that leaves us standing at the edge of a great mystery where the very concepts of space and time as we know them begin to blur and break down. And perhaps that is not a flaw in our understanding, but an invitation to simply wonder at the profound and beautiful strangeness of our universe. But the universe doesn't stop there. It seems to delight in pushing these concepts to their absolute limits. If a neutron star is an engine of cosmic extremes, then a magnetar is the version with the accelerator pedal pushed all the way to the floor. These are a rare and exceptionally violent type of neutron star, distinguished by their magnetic fields that are not just millions, but trillions of times stronger than Earth's. They are among the most intense magnetic fields of any known astronomical object, and this incredible intensity gives rise to a series of extraordinary and peculiar phenomena. One of the most striking is the emission of giant flares or bursts of gamma rays and X-rays that can unleash more energy in a fraction of a second than our sun emits in tens of thousands of years. These cosmic outbursts are believed to be caused by the instability and restructuring of the Magnetar's magnetic field. Imagine the star's crust as a brittle surface being twisted and stressed by this impossibly powerful magnetic field. When the stress becomes too great, the crust cracks and the magnetic field violently reconfigures itself, releasing a colossal torrent of energy. We call these events starquakes, a name that beautifully captures the seismic violence of this celestial object. These cosmic temblors can dramatically alter the Magnetar's rotation speed and magnetic alignment, a telltale sign of the profound forces at work within. The discovery and study of these magnetars have profoundly enriched our understanding of the universe, offering a glimpse into the behavior of matter and magnetic fields under conditions that are simply impossible to replicate on Earth. They are a reminder that the cosmos holds a diversity and extremity of objects far beyond our initial imaginings. Their study not only advances our understanding of astrophysics, but also pushes the broader quest to understand the fundamental forces that shape our universe. They are a strange, beautiful, and violently active piece of the cosmic puzzle, a testament to the fact that even within the known categories of celestial objects, there is always room for the unexpected and the extreme. And from these quiet, spinning, violent titans, we now turn our gaze outward toward a class of objects so luminous they can be seen from across the observable universe. We whisper their name now, blazars. These are a special kind of active galactic nuclei, or AGN, which are the brilliant energetic cores of galaxies. At their heart, they are powered by a supermassive black hole, much like the one we drifted to earlier. But what sets a blazar apart is a matter of perspective, of cosmic alignment. Imagine a supermassive black hole at the center of a galaxy greedily devouring material that spirals into it. As the material falls in, it releases an immense amount of energy, and in some cases, creates two powerful narrow jets of charged particles that are ejected from the poles of the black hole at nearly the speed of light. Now picture our own Earth far, far away. In most AGNs, these jets are aimed off to the side and we see them from an angle. But in a blazar, one of these jets is pointed almost directly at us, like a cosmic flashlight shining right in our eyes. This perfect alignment creates a spectacular display of light and energy. The process is called relativistic beaming, and it makes blazars incredibly luminous across the entire electromagnetic spectrum. From radio waves to high-energy gamma rays, they can outshine their entire host galaxy, a testament to the immense power being unleashed by the supermassive black hole at their core. Their emissions can fluctuate dramatically, changing their brightness over periods of minutes to years, which tells us that highly dynamic and energetic processes are at work. Blazars are key sources of high-energy gamma rays, the most energetic form of electromagnetic radiation. The mechanisms that produce such extreme energy are still a subject of research, but they are thought to involve a complex ballet of particles in the jets spiraling in magnetic fields and colliding with low-energy photons to produce a stupendous amount of energy. The study of blazars not only helps us understand the extreme conditions near supermassive black holes, but also provides a window into the evolution of galaxies and the behavior of matter under extreme gravity. They serve as crucial cosmological probes, illuminating the intervening space and giving us clues about the structure of the universe on a large scale. By observing these objects, we are peering billions of light years away, seeing them as they were in a much younger universe. This allows us to test the limits of our knowledge about the universe's fundamental laws, pushing the boundaries of our comprehension of the cosmos. Blazars, in their beautiful and violent alignment, are a profound reminder that sometimes the most astonishing secrets are revealed not in their entirety, but in a fleeting glimpse, a perfectly aimed beam of light that travels through the quiet darkness for billions of years, just to find us. Let us now gently turn our gaze from the tangible, though extreme objects we can glimpse with our instruments and drift into the realm of the truly invisible, the mysterious forces and elusive substances that weave the very fabric of our universe, yet remain hidden from our direct sight. Imagine a vast cosmic ocean. We see the waves, the foam, the ships sailing across its surface, but beneath in the deep dark currents, there are unseen forces at work, shaping everything we observe. This is where we begin our quiet exploration of dark matter. For decades, astronomers have observed the universe with increasing precision, mapping galaxies, clusters of galaxies, and the intricate sprawling cosmic web that connects them all. Yet a perplexing problem consistently emerged from their calculations. There simply isn't enough visible matter. The stars, planets, gas, and dust that we can detect with our telescopes to account for the gravitational effects we observe. Galaxies spin too fast, their outer stars moving at speeds that should fling them apart into the void. Galaxy clusters hold together with a tenacity that visible matter alone cannot explain. It's as if there's an unseen dancer gracefully guiding the cosmic ballet, providing the necessary pull, but remaining entirely out of sight. This unseen gravitational influence led scientists to hypothesize the existence of dark matter. It is a type of matter that doesn't emit, absorb, or reflect any electromagnetic radiation, meaning it's completely invisible to every kind of telescope we possess, from radio waves to X-rays and gamma rays. We know it's there only through its gravitational tug, like feeling the presence of an invisible giant by the way it pulls on everything around it. It's estimated to constitute approximately 85% of all the matter in the universe, an astonishing realization that means everything we can see, everything we are made of, is but a tiny luminous fraction of the cosmos. The mysterious nature of dark matter lies precisely in its elusive interactions. Unlike the baryonic matter, the ordinary stuff that makes up stars, planets, and even ourselves, dark matter, simply doesn't seem to care about light. It doesn't scatter, it doesn't absorb it, doesn't glow with it. This makes it incredibly challenging to detect directly. Scientists have proposed several hypothetical particles as candidates for dark matter names that sound like whispers from a hidden realm. Weakly interacting massive particles, WIMPs, axions, and sterile neutrinos. Massive experiments deep underground to shield them from cosmic noise are patiently listening for the faintest whisper of a dark matter particle colliding with an ordinary one. Giant particle accelerators like the Large Hadron Collider are trying to create them, but so far the direct detection remains elusive, a silent challenge that reminds us how much more there is to learn about the fundamental ingredients of our cosmic home. This ongoing quest for dark matter is one of the most active areas of research in both cosmology and particle physics. Its discovery would resolve many mysteries regarding the universe's formation and structure, illuminating how galaxies came to be and how they hold together across vast cosmic timescales. But what if the answer isn't a particle? What if it requires a fundamentally new kind of physics, a transformation in our understanding of the universe's foundational forces? This question itself is a beautiful testament to the humbling nature of science. We stand at the precipice of discovery, knowing that a vast unseen ocean of influence surrounds us, waiting for us to find the right way to see it. And just as we begin to ponder the vast unseen ocean of dark matter, we encounter an even more profound and perplexing mystery, one that acts not as a cosmic glue, but as a cosmic propeller. Let us gently shift our focus now to dark energy. Imagine again our cosmic ocean, but this time, the ocean itself is not only vast, but is mysteriously expanding, and not just expanding, but speeding up its expansion with every passing moment. For most of the 20th century, cosmologists generally assumed that the universe's expansion, set in motion by the Big Bang, would be gradually slowing down. The collective gravitational pull of all the matter within it, both visible and dark, should act like a cosmic brake slowly decelerating its outward rush. But then, at the close of the 20th century, a profound shock rippled through the scientific community. Two independent research teams studying distant exploding stars called Type Ia supernovae, which act as incredibly reliable standard candles for measuring cosmic distances, discovered something astonishing. The universe was not decelerating. It was accelerating. This startling revelation implied the existence of a previously unknown energy component, something that was exerting a repulsive pressure, actively pushing space apart and counteracting the attractive pull of gravity. This entity, reflecting its mysterious and elusive nature, was named any dark energy. It doesn't emit, absorb, or reflect light, making it completely invisible, just like its dark matter cousin. We infer its presence and properties only through its large-scale gravitational effects on the universe's expansion. It's like witnessing a magnificent ship picking up speed in open waters, even though its sails are down and its engines appear silent. We know something is propelling it, but we cannot see the mechanism. Dark energy is estimated to account for approximately 68% of the total energy density of the universe, an even larger slice of the cosmic pie than dark matter. This means that nearly 3/4 of our entire universe is made of something we cannot see, something we do not understand. This realization necessitated a radical overhaul of cosmological models, fundamentally reshaping our understanding of the universe's ultimate fate. Before dark energy, the universe's destiny was thought to be a simple choice: expand forever, slow down and stop, or eventually collapse in a big crunch. Now, with dark energy actively pushing everything apart at an ever-increasing rate, a new unsettling scenario emerges. The universe could continue expanding indefinitely, eventually stretching galaxies, stars, and even matter itself into a diffuse, cold, and utterly lonely expanse known as the Big Rip. The leading theory about dark energy suggests that it might be a property of space itself, inherent in the very vacuum. This idea aligns with Einstein's cosmological constant, a term he once introduced into his equations of general relativity to allow for a static universe, and later discarded as his biggest blunder when the universe's expansion was discovered. Perhaps Einstein was right in a different way all along. Quantum theory, with its whispers of virtual particles constantly flickering in and out of existence in empty space, hints at a vacuum that is not truly empty, but filled with a restless hum of energy. Yet there's a perplexing discrepancy. Theoretical predictions for this vacuum, energy's density, are vastly, incredibly larger than what astronomical observations of dark energy imply. This gap is one of the deepest mysteries in physics, a chasm between our theories and the reality of the cosmos. Understanding dark energy is not only crucial for cosmology, but for fundamental physics, as unraveling its nature could lead to new insights into the forces and particles that compose our universe, perhaps even the very fabric of space and time itself. Let us now journey back in time to the very first moments of the universe, a period so brief, so intense, that it defies our everyday understanding. Imagine a time when the entire observable universe was smaller than a proton, a tiny speck of pure potential. And then, in less than a blink of an eye, in a fraction of a second, so minuscule, it's hard to conceive, this primordial speck exploded outward, not into space, but as an expansion of space itself. This is the theory of cosmic inflation, a period of incredibly rapid exponential expansion that occurred immediately after the Big Bang. This dramatic burst of growth from a size smaller than an atom to a macroscopic scale in an unimaginably short time served as the universe's grand smoothing mechanism. Think of a tiny crumpled piece of paper. If you were to blow it up exponentially, suddenly making it vast, any wrinkles or folds on its surface would be stretched out and smoothed away, becoming imperceptible across the grand new scale. This is how inflation provided a compelling explanation for the flatness problem, why space appears to be so incredibly close to geometrically flat on large scales. Without inflation, the precise fine-tuning required for such flatness would be inexplicable, a cosmic coincidence too improbable to believe. Inflation rapidly expanded space, effectively flattening any curvature, just like blowing up a balloon. Smoothly expands its surface. Inflation also gracefully addressed another profound mystery, the horizon problem. This problem arises from the observation that regions of the universe that are now vastly far apart so far that light, even traveling since the Big Bang, could not have crossed the distance to equalize their temperatures, somehow have nearly the same background temperature observed in the cosmic microwave background radiation. It's as if two strangers living on opposite sides of a vast continent who have never met somehow wake up every morning with the exact same thoughts. Inflation posits that these regions were in fact once intimately connected, close enough to be in thermal equilibrium, before being violently thrust apart by the universe's sudden exponential expansion. This explained their uncanny uniformity, turning a cosmic paradox into a beautiful consequence. Moreover, cosmic inflation provided a mechanism for the generation of the primordial density fluctuations that seeded all cosmic structure formation. Imagine the universe in its infancy was not perfectly smooth. Quantum mechanics tells us that even in a seemingly empty vacuum, there are tiny fleeting fluctuations, ripples in the fabric of existence. Inflation took these microscopic quantum jitters, these incredibly tiny variations in energy and density, and stretched them to macroscopic scales. These stretched-out fluctuations became the initial patterns, the cosmic blueprints for the distribution of galaxies and other large-scale structures we observe today. It was like taking an incredibly subtle ripple in a pond and, in an instant, making it a towering wave across an ocean. By proposing a mechanism for such rapid expansion, cosmic inflation connected the seemingly disparate worlds of quantum mechanics, which governs the subatomic, and general relativity, which describes the cosmos on its grandest scales. It was a bridge between the microscopic and the macroscopic, paving the way for a deeper, more unified understanding of the universe's origins. Cosmic inflation stands as a cornerstone of modern cosmology and a focal point for theoretical physics, inspiring awe at the ingenuity of the universe's earliest moments. As we gently float through these profound ideas, we arrive at an even more ambitious vision, a grand attempt to weave all the separate threads of reality into a single, elegant tapestry. This is string theory, a theoretical framework that seeks to unify all the fundamental forces of the universe. Gravity, electromagnetism, the strong nuclear force that binds atomic nuclei, and the weak nuclear force involved in radioactive decay within a single harmonious description. Imagine the universe as a magnificent symphony. We hear the separate melodies of gravity, light, and atomic forces, each playing its own beautiful tune. String theory suggests that these are not separate instruments, but different notes played on the very same instrument. At the heart of string theory is a truly radical idea. The most basic units of the universe are not the familiar point-like particles, the electrons, quarks, and photons we've come to know, but rather tiny one-dimensional vibrating strings. Imagine these strings as incredibly minute, perhaps a billionth of a billionth of a billionth of a billionth of a meter long. These strings can be closed loops like tiny rubber bands or open strands with free ends. And just like the strings on a musical instrument, they vibrate at specific resonant frequencies. The magic of string theory is that the particular way a string vibrates its unique note determines the properties of the particle, it represents its mass, its charge, and how it interacts with other particles and forces. So in this cosmic symphony, the different vibrations of these fundamental strings effectively become the particles we observe. A certain vibration might be an electron, another might be a photon, another a quark. The true innovation of string theory lies in its ability to naturally incorporate gravity, a challenge that has plagued quantum field theories for decades. General relativity. Our best description of gravity works beautifully on large scales, describing the curvature of space-time around massive objects. Quantum mechanics, on the other hand, describes the subatomic world. But when physicists try to combine them, the equations break down, leading to insurmountable mathematical difficulties. String theory, however, includes a type of vibration that elegantly describes gravity, offering a potential path to a quantum theory of gravity, a unified framework where the gentle pull of gravity and the whimsical dance of quantum particles are all part of the same cosmic dance. One of the most significant and mind-bending implications of string theory is that it necessitates the existence of extra-spatial dimensions beyond the familiar three dimensions of space: up, down, left, right, forward, and backward, and one dimension of time that we experience directly. Imagine these additional dimensions not as vast open spaces, but as being compactified or curled up at incredibly tiny scales, so infinitesimally small that we haven't been able to detect them with our current technology. Think of a garden hose. From a distance, it looks like a one-dimensional line, but if you get close, you see that it has a second curled-up dimension, its circumference. In a similar way, string theory suggests that the universe might have hidden curled-up dimensions, providing a possible explanation for why we do not observe them directly in our macroscopic world. However, despite its breathtaking potential and mathematical elegance, string theory faces considerable challenges. Currently, it cannot make predictions that are specific enough to be tested with our present experimental technology. This makes it incredibly difficult to confirm or refute the theory's validity, leaving it in the realm of beautiful, unproven hypotheses. Additionally, there isn't just one string theory, but a vast landscape of possible solutions, each corresponding to different ways these extra dimensions could be curled up, potentially leading to a huge number of universes with distinct physical laws. This makes it a challenge to single out the correct description of our universe. Despite these hurdles, the pursuit of string theory has profoundly influenced theoretical physics, leading to the discovery of new mathematical tools and concepts pushing the very boundaries of our understanding of the universe. As it stands, string theory represents the forefront effort in the quest to realize Einstein's dream of a theory of everything, a single eloquent description that beautifully explains the workings of the cosmos in its entirety. It is a gentle reminder that some of the deepest truths might be found not in simple answers, but in the elegant complexity of the questions themselves, leading us further into the beautiful unknown. Now let us take another gentle turn into an idea that is so profoundly strange, it might just reshape how we think about reality itself. Imagine not just what is in a volume of space, but what might be on its very boundary. This is the holographic principle, a revolutionary concept in theoretical physics that emerged from our deepest attempts to unify the giant, graceful dance of general relativity with the tiny, whimsical jig of quantum mechanics, particularly through the study of black holes. This principle suggests something truly mind-bending. All of the information contained within a three-dimensional volume of space can be represented as a hologram encoded on a two-dimensional surface that acts as its boundary. Think of a credit card with a hologram on it. The image on the card appears three-dimensional, but all the information is actually stored on a flat two-dimensional surface. The holographic principle posits that our entire three-dimensional reality, with all its galaxy stars, and even ourselves, might in some sense be a projection, a grand cosmic illusion derived from information stored on a distant two-dimensional boundary. This idea was first proposed in the 1990s by physicist Leonard Susskind, inspired by the profound work of Gerard 't Hooft and building upon Stephen Hawking's groundbreaking research on black hole radiation. At its core, the holographic principle challenges our conventional understanding of how space and information are organized. Traditionally, we assume that the volume of space itself is where all physical processes take place, where all information is stored like a vast cosmic library. However, the holographic principle suggests that the fundamental description of the universe is inscribed not within the space, but on a boundary to that space, hinting at a deeper layer of reality, where the universe is essentially a projection of this two-dimensional information. One of the most compelling aspects of the holographic principle comes from its implications for black holes. 't Hooft and Susskind realized that the information content of a black hole is proportional not to its volume, but to the area of its event horizon, its two-dimensional surface. This was a startling insight, suggesting that the black hole wasn't swallowing information and losing it forever, as some theories implied, but rather encoding it on its boundary like a cosmic hard drive. This elegantly resolves the paradox of information loss in black holes, suggesting that information is not lost, but encoded on the event horizon, thereby reconciling quantum mechanics and general relativity's predictions about these enigmatic cosmic devourers. But the holographic principle has profound implications far beyond black holes, offering an entirely new way of thinking about the very fabric of the universe. It implies that what we experience as three-dimensional reality is, in some sense, an emergent phenomenon from underlying two-dimensional information. This conceptual shift has the potential to fundamentally change our understanding of space-time and matter. It's like discovering that the intricate flowing patterns on a river's surface are simply reflections of deeper unseen currents, and that the true story of the river is told not just by the ripples we see, but by the fundamental forces that shape its depths. In practice, the holographic principle has fueled significant developments in theoretical physics, particularly in string theory and quantum gravity. It is at the heart of the AD-S-CFT correspondence, a profound conjecture that offers the most concrete realization of the holographic principle by relating a gravitational theory in a specific type of spacetime called anti-de Sitter AD-S space to a quantum field theory CFT on its boundary. Though the full implications of the holographic principle are still being explored, it stands as a pivotal insight into the nature of reality and the quest for a unified theory of everything, symbolizing a radical shift in our understanding of the universe's fundamental structure. It's a concept that invites us to lie back, close our eyes, and simply wonder if the very reality we inhabit is a grand, shimmering hologram, a cosmic projection of secrets yet to be fully deciphered. As we continue our gentle journey through the cosmic night, having touched upon the hidden matter and the accelerating push of our universe, let us now allow our minds to playfully wander into perhaps the most mind-bending concept of all, the idea that our universe might not be the only universe. Imagine our vast cosmos with all its shimmering galaxies, ancient stars, and swirling nebulae as just a single precious droplet in an immeasurable, perhaps infinite cosmic ocean. This ocean is known as the multiverse, and within it, countless other universes, each a unique droplet, may exist, differing in size, structure, and perhaps even in the very laws of physics that govern them. This proposition, once confined to the vibrant imaginations of science fiction writers, has surprisingly pivoted into a serious scientific hypothesis. The support for this idea doesn't come from direct observation, for how could we possibly glimpse another universe? Instead, it arises from the theoretical groundwork and indirect evidence that suggests the possibility of their existence, like listening to a faint echo that hints at a larger, unseen cavern. One of the most intriguing whispers comes from the strange realm of quantum mechanics. Here, the many worlds interpretation posits something truly astonishing, that for every possible outcome of a quantum measurement, the universe splits, creating a separate, non-communicating branch of reality where each outcome actually occurs. Imagine standing at a crossroads. In our everyday experience, you choose one path, but in the many worlds interpretation, every path you could have taken, every choice you could have made, exists in a separate parallel universe. This suggests a vast, possibly infinite number of parallel universes where every conceivable outcome to every decision or quantum event, no matter how small, truly exists. It's as if reality is constantly blossoming into countless new branches, each one a universe unto itself. Another powerful theoretical foundation for the multiverse arises from the theory of cosmic inflation that we gently explored earlier. The very mechanism that smoothed out our own universe and made it so vast and uniform after the Big Bang also allows for the possibility of an infinite number of bubbles or pocket universes within an ever-expanding, larger multiverse. Imagine baking an enormous cosmic loaf of bread, and as it rises, countless little air bubbles form within it, each one expanding and separating from the others. Each of these bubble universes might have its own unique physical constants and laws of physics leading to drastically different environments from our own. Perhaps in one gravity is so strong that stars collapse into black holes instantly. In another, it's so weak that galaxies can't even form. This view suggests that our universe is simply one of these bubbles floating within a much larger, eternally inflating sea of possibilities. Then there are the whispers from string theory, with its landscape of possible solutions. As we gently learned, string theory suggests the existence of extraspatial dimensions that are curled up at incredibly tiny scales. But there's not just one way for these extra dimensions to curl up. There are theoretically an almost unimaginable number of ways, a landscape of solutions, each corresponding to different ways these dimensions could be compactified. Each different compactification could give rise to a universe with its own unique set of physical laws and fundamental constants. This paints a picture of a vast number of universes, each with its own distinct flavor of physics and depending on how its hidden dimensions are structured. And for the truly adventurous mind, there's the mathematical universe hypothesis, a more abstract and philosophical notion. It suggests that any mathematically consistent structure or universe must exist just as real as our own. This broad conceptual framework implies the existence of an almost unimaginable variety of universes, each with its unique set of laws and constants, because if it can be described mathematically, then perhaps it exists somewhere. These parallel universes, if they exist, could differ from our own in countless ways, far beyond our current imagination. They might feature different physical constants, for example, the strength of gravity or the electromagnetic force. This could lead to universes where stars and galaxies, or even life as we know it, simply cannot form. Other universes might have a different number of spatial dimensions. Imagine a universe with 2 spatial dimensions, flat as a pancake, or one with 5, where movement is utterly baffling to our 3-dimensional minds. Or they could have entirely different laws of physics, leading to realms that are unimaginably alien, where the very concept of time might flow in reverse, or where particles interact in ways we cannot even begin to conceive. While these ideas are deeply fascinating and form the basis for much speculative thought and some serious scientific research, it's crucial to emphasize that the concept of parallel universes remains for now speculative without empirical evidence. We have no telescope that can peer into another universe, no experiment that can detect its presence. As such, they prompt as many philosophical questions as scientific ones, challenging our understanding of reality and pushing the very boundaries of what we consider possible in our quest to understand the cosmos. The multiverse, for all its grandiosity, remains a whisper in the dark, a beautiful hypothesis waiting for a definitive sign. Now let us turn our minds to a phenomenon that feels less like a grand theoretical construct and more like a whispered secret between the tiniest inhabitants of the universe, a phenomenon that seems to mock our conventional understanding of space and time. This is quantum entanglement, a truly eerie synchronization between particles that acts as a rebel of the cosmic order we've come to accept. In the strange and whimsical realm of quantum physics, 2 particles can become entangled in such a way that the state of one, no matter the distance from its partner, instantly correlates with the state of the other. Imagine 2 perfectly synchronized coins. You flip one and it lands on heads. Instantly, across any distance, its entangled partner, without any communication, is guaranteed to be tails. If the first is tails, the second is heads. It's as if they share a secret instantaneous connection that transcends the vastness of space. This instantaneous connection, famously derided by Einstein as spooky action at a distance, defies the universal speed limit set by the speed of light. Light, the fastest thing we know, still takes time to travel from one point to another. But the information between entangled particles seems to arrive without delay, suggesting that their connection is not bound by the conventional flow of time or the vastness of space. This challenges our deep-seated notions of causality and locality, the principles that have anchored the scientific community's understanding of the universe for centuries. Causality suggests that an effect must have a cause that precedes it, and locality suggests that objects only influence their immediate surroundings. Entanglement seems to gently but firmly break these rules. If we take a step back and ponder this defiance, quantum entanglement nudges us towards a realization that the fabric of the universe might be far more interconnected than our everyday experiences, and the classical physics of billiard balls suggest. It hints at an underlying layer of reality where the concept of separate distinct objects, influenced only by their physical separation, might be just an illusion. These entangled quantum entities share a bond that transcends the spatiotemporal constraints imposed by the speed of light, suggesting that the true nature of the cosmos is woven together by threads of interconnectivity that eluded our traditional understanding. It is a whisper from the deep, reminding us that reality is far stranger and more beautiful than we could ever imagine. This phenomenon, while ethereal and profoundly complex, offers a tantalizing glimpse into the enigmatic underpinnings of our universe. It beckons us to rethink the very essence of space-time and reality itself. Scientists are now actively exploring how to harness this spooky action for technologies like quantum computing and quantum communication, pushing the boundaries of what is possible. But even without immediate applications, the sheer mystery of entanglement serves as a profound lullaby, inviting us to contemplate a universe where connections run deeper than we can perceive, a universe bound by invisible, instantaneous threads that weave it all together in a silent, cosmic dance. From the instantaneous, almost magical connections of quantum entanglement, let us now shift our focus to an idea that scrutinizes the very texture of space itself. Imagine that space is not a smooth, infinitely divisible canvas, but rather a meticulously woven fabric made of tiny, discrete stitches. This is the daring proposition of loop quantum gravity LQG, a theory that emerges as a challenger to our traditional understanding of the universe's fabric, offering an alternative to the mainstream quest for a theory of everything, like string theory. Loop quantum gravity suggests that space itself is not a smooth, continuous expanse, as depicted by Einstein's elegant theory of relativity. Instead, it is composed of tiny, discrete loops, like an incredibly fine three-dimensional chainmail. Think of the universe not as a continuous flowing sheet of silk, but rather as being woven from a fabric of looped threads, with each loop representing an extremely minute quantized bit of space. This quantization of space implies that there is a fundamental, smallest possible distance, a cosmic pixel below which space simply cannot be divided further. This contrasts sharply with the classical view that you can divide distances infinitely, zooming in forever without reaching a fundamental limit. In LQG, the universe at its most fundamental level is not infinitely smooth, but granular, like a pointillist painting seen from very, very close up. This granular view of the cosmos reshapes our understanding of gravity itself. The traditional view from general relativity sees gravity as a curvature of space-time dictated by the presence of massive objects, like a bowling ball causing a dip in a stretched rubber sheet. Loop quantum gravity enriches this view by adding a quantum layer where space-time itself has a granular atomic structure. This means that gravity, too, emerges from the interactions of these fundamental loops of space. It's like understanding that the smoothness of a large body of water is an illusion created by countless tiny individual water molecules. This fascinating perspective also offers promising avenues to solve some of the most enduring paradoxes in physics, particularly concerning black holes and the Big Bang. In the realm of loop quantum gravity, the dreaded singularities, the points of infinite density and zero volume thought to exist at the center of black holes and at the origin of the Big Bang, are surprisingly replaced by something less extreme. Instead of collapsing into an infinitely dense point matter falling into a black hole, might under the principles of LQG bounce through a bridge to another universe or perhaps to another region of our own. Similarly, the Big Bang might not have originated from an infinitely dense point, but from a big bounce from a previous contracting universe. This offers a gentle, less violent image of creation where the universe does not end in a crushing singularity, but in a graceful transition, a perpetual cosmic dance of expansion and contraction. Such a perspective not only challenges the traditional views of space and time, but also provides a tantalizing way to marry the quantum world with the cosmological in a way that respects both scales. It paints a picture of a universe not as a smooth continuum, but as a mosaic of finite quanta urging us to re-examine the very fabric of reality itself. Loop quantum gravity invites us to imagine that the calm, vast expanse we see above us is at its deepest level, a shimmering, intricately woven tapestry of countless tiny threads, each one a fundamental piece of the universe's grand design. It's a beautiful thought to hold as we drift off, pondering the hidden texture of everything. And now let's dive even deeper into a concept that pushes the limits of our imagination, suggesting that the very fabric of the universe, at its most fundamental scale, is not just granular, but alive with a restless, chaotic energy. This is space-time foam, one of the most intriguing and mind-bending concepts in modern theoretical physics. Imagine a seemingly calm ocean. From a distance, its surface appears smooth and continuous. But as you get incredibly close, perhaps with a microscope, you start to see countless tiny bubbles constantly popping into and out of existence, creating a frothy, turbulent surface. Space-time foam suggests that the fabric of the universe itself is like this, but at the incredibly minuscule Planck scale, the smallest scale of distance and size relevant to the physics of the quantum world, approximately 10 to the power of minus 35 meters. At this unimaginable tiny scale, space-time is predicted to be turbulent and frothy, much like the foam on a cappuccino. This tumultuous state arises from the inherent quantum fluctuations in the fabric of space-time itself. Quantum mechanics, with its principle of uncertainty, tells us that even in a perfect vacuum, energy cannot remain perfectly still. Instead, tiny virtual particles constantly pop in and out of existence, flickering into being for an infinitesimally brief moment before vanishing again. Space-time, in response to these ephemeral particles and the inherent uncertainty of quantum reality, bends, twists, and ripples in a constant, restless chaos. It's as if the very stage upon which the universe plays out its drama is itself a constantly churning, frothing entity at its most fundamental level. This foamy nature of space-time at its minutest scales implies strange properties and behaviors that stand in stark contrast to our everyday experiences and understanding of the universe. For instance, the concept challenges the very notion of precise, fixed locations and distances. If the fabric of space-time itself is in constant fluctuating chaos at the Planck scale, then how can we speak of a truly definite point or a fixed distance between 2 points? It's like trying to measure the exact distance between 2 bubbles on a constantly churning froth. The measurement changes with every fleeting moment. Moreover, space-time foam suggests that the familiar concepts of time and space lose their precise meaning at the most fundamental level of the universe's structure, forcing physicists to rethink the very foundations of reality itself. What does it mean for space to be foamy? It means that our smooth, predictable reality emerges only at larger scales. Much like the smooth surface of the ocean is an average of countless individual waves and ripples. One of the most fascinating implications of space-time foam is its potential to reconcile the seemingly incompatible theories of general relativity and quantum mechanics. By introducing a quantized granular structure of spacetime, it offers a bridge between the very large, the cosmological scales described by general relativity, and the very small, the subatomic particles governed by quantum mechanics. It provides a glimpse into a unified understanding of the universe where the two pillars of modern physics might finally meet in a harmonious dance. Although direct evidence of spacetime foam remains elusive, its investigation pushes the boundaries of theoretical physics, promising to unlock secrets of the cosmos that could revolutionize our comprehension of the universe and its underlying principles. It's a concept that leaves us with a profound sense of awe, imagining that beneath the calm grand expanse of the night sky, there is an invisible tumultuous froth of reality, a place where the universe itself is forever in motion, constantly creating and uncreating its own deepest fabric. It is a mystery that invites us to simply wonder at the profound and beautiful strangeness of everything. Now, as we gently return from the deep hidden textures of spacetime, let us settle on a question that has long puzzled humanity, a question that feels both intimate and impossibly vast, a question about loneliness in the cosmos. This is the Fermi paradox, a tantalizing contradiction in our quest to understand our place in the universe. On one hand, given the vast, unimaginable number of stars in our Milky Way galaxy alone, hundreds of billions of them, many of which are orbited by planets, and many of those planets residing in the habitable zone, where conditions for life as we know it could exist, the expectation would naturally be that the universe should be teeming with civilizations. The cosmic stage seems perfectly set for an endless play of diverse life forms. Yet, on the other hand, we find a perplexing silence. Despite decades of patiently scanning the heavens for signals of sending probes to the farthest reaches of our solar system, we have yet to uncover definitive, undeniable evidence of extraterrestrial life, intelligent or otherwise. No radio messages, no strange lights, no obvious cosmic megastructures. The silence is deafening. This paradox, first articulated by physicist Enrico Fermi over a casual lunch with colleagues in 1950, challenges our understanding and expectations about the universe. He simply asked, "Where is everybody?" A question that is deceptively simple, yet profoundly unsettling. Fermi's query delves into the very heart of our quest for extraterrestrial intelligence, juxtaposing the high probability of abundant, life-friendly environments in the galaxy against our stark lack of evidence for such life. The silence forces us to consider a wider array of explanations, each more thought-provoking than the last. Could it be that intelligent life, despite the favorable conditions, is exceedingly rare, an incredibly improbable cosmic roll of the dice? Or perhaps life, once it emerges, is inherently short-lived, doomed to self-destruct through its own technological advancements or through natural catastrophic events? Maybe civilizations, once they reach a certain level of advancement, choose to remain silent, deliberately avoiding contact for reasons we cannot fathom. Or perhaps the vast distances between stars are simply too immense, making interstellar travel or communication too costly and time-consuming, preventing any widespread network of civilizations from forming. Some more speculative ideas suggest that advanced civilizations might be so different from us that we simply wouldn't recognize their signals. What if their technology operates on principles so alien to our own that our radio telescopes are simply deaf to their whispers? Or perhaps there's a great filter ahead of us, some insurmountable obstacle that almost all civilizations encounter before they can spread across the galaxy, a filter that we might yet face. The Fermi paradox is a concept that both humbles and intrigues, urging us to contemplate the myriad factors that could contribute to the apparent loneliness of our civilization in the universe. It serves as a gentle reminder of the vastness of the unknown and the limits of our current perception. Through its unresolved nature, the Fermi paradox continues to fuel intense research and debate across multiple disciplines from astrophysics to biology and even philosophy. It underscores the profound mystery of our existence within the vast tapestry of the cosmos, reminding us that sometimes the most important answers are not found, but simply patiently waited for in the quiet, expansive silence of the night sky. As we gently float through the quiet expanse of the cosmos, having pondered the invisible forces that shape it and the grand theoretical notions of multiple universes, let us now turn our attention to the more tangible, yet equally astonishing wonders that orbit other stars. For centuries, our understanding of planets was limited to the familiar family within our own solar system, the rocky inner worlds, the gas giants in their stately distant orbits. We assumed this was the norm, the cosmic blueprint. But then a quiet revolution began with the discovery of exoplanets, planets orbiting stars beyond our sun, and they quickly showed us just how much more diverse and surprising the universe truly is. Imagine the gentle surprise that rippled through the astronomical community when the very first exoplanets were definitively confirmed in the 1990s. One of the most unexpected discoveries was a type of planet we now affectionately call hot Jupiters. Imagine a gas giant, a swirling behemoth of hydrogen and helium, much like our own Jupiter. But instead of orbiting its star in a cool, distant path, it hugs its sun so closely that its surface temperatures blaze, often exceeding 1,000 degrees Celsius. It completes an orbit, not in years, but in mere days, sometimes even hours. This was utterly contrary to the existing theoretical models of planetary formation, which suggested that gas giants with their massive icy cores should form in the colder outer regions of a star system, far from the searing heat of their parent star. The existence of hot Jupiters immediately challenged our understanding, suggesting a dynamic and complex process of planetary migration where these massive worlds somehow formed far out and then spiraled inward, or perhaps formed in situ under extreme conditions. It was as if the universe, with a playful wink, decided to show us that our assumptions were far too narrow and that planetary systems could be arranged in ways we had never anticipated. This unexpected existence of hot Jupiters stirred deep questions about the uniqueness of our solar system's architecture. Was our neatly ordered cosmic home with its inner rocky planets and outer gas giants a rarity? Or were these blazing close-in giants just one facet of a much grander, more varied cosmic design? The discovery of hot Jupiters was a landmark moment ushering in a new era of exoplanet research and driving astronomers to develop novel theories of planetary formation and migration. It was a gentle, yet firm reminder that the cosmos often harbors phenomena beyond our most imaginative predictions, continually expanding our understanding of the universe, one surprising planet at a time. Now let's turn our attention to another captivating category of exoplanets that has profoundly broadened our understanding of planetary diversity across the cosmos: super-Earths. These planets occupy a unique position in the cosmic pantheon, defined by their mass and size being larger than Earth, but smaller than the ice giants like Uranus and Neptune. They typically range from 1 to 10 times the mass of our own humble Earth. Imagine a world that feels familiar yet grander, a place where gravity might be a little stronger and the skies might look subtly different. Their significance in the ongoing search for extraterrestrial life stems from several intriguing factors. Firstly, their larger size and mass mean that under the right conditions, they could retain substantial atmospheres for billions of years, perhaps even thick enough to protect their surfaces from harmful stellar radiation. These atmospheres could potentially contain gases indicative of biological processes like the oxygen and methane that fill our own sky, hinting at a bustling ecosystem below. Secondly, and perhaps most tantalizingly, many super-Earths are believed to be rocky worlds like our own planet. And crucially, some have the potential for harboring liquid water on their surfaces. We often look for water as a key ingredient for life as we know it, a solvent, a medium for chemical reactions. The existence of super-Earths in the habitable zone of their stars, that optimal distance where temperatures could allow for liquid water to exist, brings a profound sense of optimism about the chances of finding environments beyond our solar system where life might thrive. It's like finding countless new potential homes in a vast cosmic neighborhood, each one holding a whispered promise, Moreover, super-Earths appear to be remarkably abundant in our galaxy. This prevalence significantly increases the likelihood of detecting signs of life or habitability within these diverse worlds, making them prime targets for future observations. Their discovery has triggered a shift in the exoplanet research focus, driving technological advancements in telescopes and observation techniques to delve deeper into their atmospheres and surface conditions. This quiet quest not only expands our knowledge of planetary formation and evolution, but also brings us one step closer to answering the profound and ancient question, are we truly alone in the universe? The super-Earths, with their whispered promises, are a gentle beckoning towards that answer. And what if the promise of water on these distant worlds isn't just a surface shimmer, but an entire, deep, encompassing reality? Let us gently imagine now water worlds or ocean planets, celestial bodies where water dominates entirely, painting a picture of planets where landmasses are either entirely absent or completely submerged beneath vast global oceans. Unlike our Earth, where land masses cover about 30% of the surface water worlds, are envisioned to have their surfaces entirely or almost entirely covered by deep oceans. These watery realms could extend for tens or even hundreds of kilometers in depth, far surpassing Earth's own maritime abysses, creating a profound blue silence that stretches into the unknown. The unexpected features of these aquatic planets stretch our imagination and challenge our understanding of habitability. One intriguing possibility is the existence of exotic forms of ice. Given the immense pressures found in the deep oceans of water worlds, water might exist in phases of ice that do not naturally occur on Earth's surface. Imagine ice that remains solid even at high temperatures, compressed into incredibly dense forms like ice Seventh, which can be found near a planet's core. This exotic ice could form a boundary between the deep ocean and the rocky mantle below, creating a layering effect with profound implications for the planet's geology and its potential to harbor life. It's like discovering that beneath the familiar surface of water, there are hidden crystalline structures holding their own secrets. Another fascinating aspect of water worlds is their potential for life. While the deep dark oceans might lack the sunlight-driven photosynthesis foundational to Earth's surface food chains, life could possibly thrive around hydrothermal vents on the ocean floor, much as it does in some of Earth's deepest, darkest waters. These vents, spewing hot mineral-rich fluids, could provide the necessary heat and chemical energy to support complex ecosystems, suggesting that life could find a foothold in environments vastly different from those on Earth. It's a reminder that life is incredibly resilient and adaptable, able to flourish in the most unexpected corners of the cosmos, finding sustenance in chemical reactions, rather than sunlight, embracing the eternal night of the deep. The study of water worlds extends beyond the immediate quest for life, offering invaluable insights into the diversity of planetary systems and the very formation of celestial bodies. Their distinct characteristics challenge our Earth-centric models of habitability and open up a wider vista in the search for extraterrestrial life, hinting at the incredible diversity that may lie hidden within the cosmos. Imagine drifting through the silent blue depths of such a world, surrounded by light from bioluminescent creatures, a soft ethereal glow in the perpetual twilight. It's a profound thought that our universe might hold countless such deep, watery secrets, waiting patiently for us to hear their quiet song. And from worlds covered in liquid, let us now imagine a world built of solid, sparkling treasure. This is the realm of a diamond planet, one of the most fascinating and exotic possibilities in the vast expanse of planetary types discovered by astronomers. The concept refers to planets that are composed significantly of carbon, and under the right conditions of immense pressure and heat, this carbon could crystallize into diamond and other exotic forms, such as graphite. Imagine gazing upon a celestial body that shimmers with the brilliance of a colossal gem, a world literally made of compressed starlight and ancient carbon. It challenges our traditional views of rocky or gas giant planets, diving deep into the realms of cosmic serendipity and extreme conditions. The formation of such exotic worlds is thought to occur under very specific and unusual circumstances. A planet would need to have a carbon-rich composition, a rarity, given the chemical diversity observed in the universe. If such a carbon-centered planet forms and then migrates close enough to its parent star, or if it undergoes intense internal heat and pressure conditions, the carbon could undergo a phase transition into diamond. It's like taking the simplest of elements and under the universe's powerful embrace, transforming it into something breathtakingly precious. One of the most discussed candidates for a diamond planet is 55 Cancri e, which orbits a sun-like star in the constellation of Cancer. Observations suggest that a significant portion of this planet's mass could be carbon, possibly in diamond form, due to the planet's high temperature and pressure conditions. This planet, sometimes called a super-Earth, as we just gently explored, takes the concept of a rocky world to an entirely new extreme. It's a reminder that the universe, in its boundless creativity, can fashion worlds that defy our most imaginative tales. The discovery and study of diamond planets, like 55 Cancri e, provide profound insights into the diversity of planetary composition and formation. It challenges our understanding of planetary science, pushing the boundaries of what we consider possible for planetary conditions and compositions. Additionally, these discoveries have implications for our knowledge of the cosmos's resources, suggesting that the universe's wealth of materials and phenomena far exceeds the confines of our earthly experiences. The study of diamond planets not only captivates the imagination, but also propels the field of exoplanet research into new and uncharted territories, promising a future rich with astonishing discoveries. It's a quiet whisper that even the most mundane elements under the right cosmic crucible can be transformed into something truly extraordinary, a testament to the universe's endless capacity for wonder. Now let us bring our focus back to a concept that has become a cornerstone of the search for life beyond Earth, a concept that brings with it a special kind of excitement and unexpected wonder. This is the habitable zone, often affectionately referred to as the Goldilocks zone. Imagine a cozy temperate band of cosmic real estate around a star where conditions are just right, not too hot and not too cold for liquid water to exist on a planet's surface. Liquid water, as we know it, is a key ingredient for life. It is the solvent in which the intricate dance of biochemistry can occur, the medium that allows the building blocks of life to interact and form complex structures. The excitement around finding planets in this Goldilocks zone is multi-layered, rooted in the tantalizing potential for habitability and the profound prospect of finding life beyond Earth. What makes finding such planets particularly unexpected and thrilling is the sheer diversity of worlds and stellar systems we encounter within these seemingly just right zones. We've found everything from rocky worlds slightly larger than Earth, hinting at potential terrestrial landscapes, to gas giants with moons that could have subsurface oceans, each a world within a world. Each discovery challenges our preconceptions about where and how life could exist, expanding the possibilities far beyond the terrestrial template of our home planet. It's like searching for a perfect garden and finding that the most beautiful flowers can bloom in soil you never expected, under skies of 1,000 different hues. Moreover, these findings are exciting, not just for their potential implications for life, but also as they represent significant technological and methodological milestones. Just a few decades ago, the detection of any exoplanet, let alone the characterization of its atmosphere or the assessment of its habitability, was beyond our reach, a dream for future generations. Now, with advanced telescopes like the groundbreaking Kepler and the diligent TS, and in the very near future, the incredible James Webb Space Telescope, astronomers are not only identifying these planets, but are also beginning to pry into their secrets. We are learning to read the breath of distant worlds, deciphering the chemical signatures in their atmospheres, searching for the telltale signs of water vapor, or even more complex molecules. The discovery of habitable zone planets opens new chapters in the story of our universe, beckoning us with the possibility that we are not alone. It represents the convergence of curiosity technology and sheer cosmic chance, where each new finding is a step closer to answering age-old questions about life's existence beyond our solar system. This quest resonates with a fundamental human desire to understand our place in the universe, making every discovery in the habitable zone a beacon of hope and a testament to our ceaseless quest for knowledge. It's a quiet, hopeful whisper in the dark, reminding us that the universe is vast and its secrets are slowly, gently revealing themselves. Now let us peer into one of the cleverest ways astronomers uncover these distant worlds, a method that reveals the presence of planets not by seeing them directly, but by noticing the subtle shadow they cast. This is the transit method, a powerful tool in the exoplanet discovery arsenal, revealing the existence of worlds beyond our solar system, in a way akin to cosmic silhouettes passing in front of distant stars. Imagine a tiny ant crawling across the face of a giant light bulb, far, far away. You wouldn't see the ant itself, but you might notice a fleeting, almost imperceptible flicker in the light, a tiny dimming as it passes. This is precisely how the transit method works. When a planet transits or crosses in front of its host star from our viewpoint, it causes a slight temporary dimming of the star's brightness. This diminutive dip in light, meticulously measured by sensitive telescopes, can tell astronomers not only that a planet exists, but also provide crucial clues about the planet's size, relative to its star, and the duration of its orbit. The longer the planet blocks the light, and the deeper the dip in brightness, the larger the planet. The regularity of these transits, how often they occur, reveals the planet's orbital period, which in turn helps us determine its distance from the host star. It's a cosmic game of hide and seek, where the hidden player reveals itself through its shadow. The transit method's success lies in its elegant simplicity and the profound information it can unveil. Moreover, by analyzing how the starlight changes as it filters through the planet's atmosphere during a transit, scientists can infer the composition of the atmosphere itself. This offers tantalizing hints about the planet's potential habitability or other remarkable characteristics. Imagine the starlight as a fine, intricate perfume. As it passes through the planet's atmosphere, certain molecules will absorb specific notes of that perfume, leaving a unique chemical fingerprint. Reading this fingerprint allows us to glimpse the very air that surrounds these distant worlds. This method has led to the discovery of a staggering array of surprising planets, each challenging our understanding of planetary science. Among these are the hot Jupiters we spoke of earlier, gas giants that orbit their stars closer than Mercury does to our Sun, their very existence defying earlier models of planetary system formation. The transit method showed us just how common these unexpected behemoths truly are. Another intriguing find is that of the super-Earth's rocky planets larger than Earth, but smaller than Neptune, which occupy a category not represented in our own solar system. Some of these super-Earths are found in the habitable zone of their stars, raising exciting possibilities about surface conditions conducive to life. Perhaps the most unexpected discoveries are those of planets like those in the TRAPPIST-1 system. Here, a single dim star hosts 7 Earth-sized planets, a few of which are located squarely in the star's habitable zone. This extraordinary system, revealed by a series of precise transits, hints at the rich diversity of planetary configurations in our galaxy and beyond, emphasizing the transit method's role in pushing the boundaries of our cosmic knowledge. Through the shadows, these distant worlds cast astronomers gently unravel the mysteries of the universe, one fleeting transit at a time, a silent ballet of light and darkness. Let us now reflect on the early days of this grand exploration, the moment our eyes first truly opened to the worlds beyond our Sun. It was in the mid-1990s that astronomers, with a mixture of intense anticipation and quiet disbelief, gazed through their telescopes and for the first time definitively discovered exoplanets. These celestial wanderers, once confined to the realm of theoretical speculation, and science fiction revealed astonishing features that defied our previous understanding of planet formation and characteristics. Before these confirmed discoveries, our knowledge of planetary systems was quite naturally confined to our own solar system. This led to a very specific model: orderly, relatively circular orbits, planets neatly separated into rocky worlds close to their star and gas giants further away. It was our comfortable cosmic nest. The very first exoplanet, discovered around a main sequence, star 51 Pegasi b, in 1995, shattered this neat, comfortable model into a million glittering pieces. It was a gas giant, a planet similar in mass to Jupiter, but shockingly, it was situated incredibly close to its star, completing an orbit in just over 4 Earth days. This was the first of the hot Jupiters to be confirmed a type of planet our solar system simply does not possess. Its existence was a profound surprise, flying in the face of prevailing theories of planetary formation, which couldn't easily explain how such a massive gas giant could form so close to its star, or how it could end up in such a tight blazing orbit through processes like planetary migration. It was a cosmic curveball, forcing scientists to immediately rethink decades of accepted wisdom. As more exoplanets were discovered, the variety of planetary systems observed grew increasingly diverse, pushing the boundaries of what we thought was possible. Some systems featured super-Earths, a class of planet not present in our solar system, suggesting a common planetary type that could vary from rocky worlds to ocean worlds, or even those with thick, opaque atmospheres. Others revealed ultra-short period planets that orbit their stars in mere hours, a dizzying pace. We found tight-knit systems of multiple planets closely orbiting their stars, dancing in intricate gravitational ballets. And perhaps most mind-bending of all, we discovered free-floating planets, worlds ejected from their parent systems to wander alone through the galaxy, untethered to any star, adrift in eternal cosmic night. The discovery of exoplanets also brought to light the commonality of multi-planet systems and the existence of resonant orbits where planets have orbital periods in precise, harmonious ratios. While this phenomenon is observed in our own solar system in subtle ways, its prevalence elsewhere was not recognized as potentially common. These discoveries forced a fundamental reevaluation of planetary formation theories, emphasizing dynamic processes that can move planets from their initial birthplaces through interactions like disk migration, planet-planet gravitational interactions, and stellar tides, among others. It showed us that planetary systems are not static, but incredibly dynamic, evolving landscapes. Moreover, the hunt for exoplanets rapidly expanded to encompass the search for potentially habitable worlds, those that lie in their star's habitable zone, where conditions might allow for liquid water to exist. This endeavor has highlighted the vast range of stellar environments where life might find a foothold, from planets orbiting binary stars, where 2 suns grace the sky, to planets around ultra-cool dwarf stars, which burn dimly but for trillions of years. The discovery of exoplanets has, in essence, revolutionized our understanding of the cosmos, revealing an unexpected, breathtaking diversity in planetary systems, and pushing the boundaries of where we believe planets can form and exist. This has not only enriched our knowledge of the universe, but has also fundamentally shifted the paradigms of planetary science and astrobiology, opening new frontiers in the quiet, profound quest to understand our place in the cosmos and whether we are truly alone in this grand, beautiful expanse. As we continue our gentle contemplative journey through the vast cosmic tapestry, having marveled at the strange dance of exoplanets and the profound implications of their existence, let us now turn our gaze to the grand assemblies of stars themselves, the galaxies. These are the magnificent island universes, each holding billions, even trillions of suns, swirling in their own unique cosmic ballets. Just as we discovered a surprising diversity among planets, so too do galaxies reveal a breathtaking array of forms and behaviors, each telling a story of cosmic evolution on the grandest scales. Imagine for a moment the smallest of these stellar islands, the dwarf galaxies. These are the smaller counterparts to the colossal luminous galaxies that dominate our cosmic landscape. While our own Milky Way can boast hundreds of billions of stars, a dwarf galaxy might contain as few as 100 million. They are like cosmic pebbles compared to the mighty boulders of the universe. Despite their diminutive size, dwarf galaxies play a remarkably pivotal role in the cosmos, challenging our initial expectations with their significant contributions to galactic evolution and the enduring mysteries of dark matter. One unexpected role they play is serving as the very building blocks of larger galaxies. Imagine a grand cosmic construction project spanning billions of years. These tiny galaxies, with their gentle gravitational whispers, are gradually drawn together, merging over eons in a process sometimes called galactic cannibalism. Our own Milky Way, for example, is thought to have grown to its immense size by devouring numerous smaller dwarf galaxies throughout its history and is still in the process of consuming others. These cosmic pebbles swallowed by larger entities contribute their star's gas and dark matter, gradually forming the massive galaxies we observe today. So these seemingly insignificant structures are in fact the fundamental bricks and mortar of the universe's grand architecture. Furthermore, a truly profound and unexpected discovery about dwarf galaxies is that they are often found to be overflowing with dark matter, the elusive, invisible substance that does not emit, absorb, or reflect light, but exerts a powerful gravitational force holding galaxies together. While we still don't fully understand what dark matter is, its presence in these small galaxies is disproportionately high compared to the visible matter. Imagine a tiny gossamer web, almost invisible but surprisingly strong, holding together a handful of glittering dewdrops. The high dark matter density within dwarf galaxies provides a unique laboratory for studying this mysterious component of the universe, offering precious clues that could finally unravel the nature of dark matter and its paramount role in the structure and evolution of the universe. They are quiet whispers from the cosmic deep, reminding us that appearances can be deceiving and that the smallest players often hold the biggest secrets. Now let's shift from the quiet building blocks to something far more energetic, a spectacle that truly lives up to its name: starburst galaxies. Imagine, instead of a gentle hum, a sudden blinding flash of countless new lights igniting across a celestial city. These galaxies are a captivating spectacle in the cosmos, characterized by their exceptionally high rate of star formation. Unlike our own Milky Way, which forms stars at a more sedate pace, about one sun-sized star a year, starburst galaxies can create hundreds or even thousands of stars annually. This frenetic activity is like a cosmic fireworks show, dazzling and intense. This incredible burst of stellar birth is typically sparked by several dramatic mechanisms, often involving collisions and interactions with other galaxies. Imagine two vast, swirling cloud formations gently drifting towards each other. As they come close, their gravitational pulls begin to distort and pull at each other, compressing the gas and dust within them. This compression, like squeezing a sponge, heats up the material and creates incredibly dense regions where conditions become perfectly ripe for stars to form at an extraordinary, almost frantic rate. Additionally, the infall of fresh gas from the vast empty spaces between galaxies, the intergalactic medium, can fuel this already fiery process of star creation, adding more fuel to the cosmic fire. This intense period of stellar birth is, however, a relatively short-lived phase in the life of a galaxy. Lasting only about 10 million to a few hundred million years, it's a mere blink of an eye in cosmic terms. It's like a brilliant, fleeting performance, burning brightly, but briefly. As spectacular as they are, starburst galaxies also play a crucial role in enriching the universe. Within their multitude of newly born stars, the furnaces of nuclear fusion forge heavier elements like carbon, oxygen, and iron, which are then scattered across the cosmos when these massive stars explode as supernovae. This contributes significantly to the cosmic cycle of matter seeding new generations of stars and planets with the building blocks of life and profoundly influencing the evolution of galaxies across the ages. They are noisy, vibrant evidence that even chaos can lead to breathtaking creation. And speaking of energetic galactic cores, let us now gently approach a class of active galaxies that are distinguished by their brilliantly luminous centers, glowing with an intensity that can outshine the entirety of their host galaxies. These are Seyfert galaxies. Imagine a vast, sprawling city, and then at its very heart, a single skyscraper that radiates so much light it makes all the other buildings seem dim by comparison. That glowing heart is the hallmark of a Seyfert galaxy. At the very core of a Seyfert galaxy lies a supermassive black hole, a silent, invisible behemoth whose mass can range from millions to billions of times that of our Sun. The remarkable activity that defines these galaxies stems from the accretion of material into this black hole. As gas dust and other debris from the surrounding galaxy slowly spiral inward, caught in the black hole's relentless gravitational embrace, they form a blazingly hot accretion disk around it. Imagine a cosmic drain with water swirling faster and faster as it approaches the center, heating up with friction. The immense gravitational and magnetic forces at work within this disk heat the material to incredible temperatures, causing it to emit vast amounts of energy across the entire electromagnetic spectrum, from gentle radio waves to harsh penetrating X-rays. Moreover, Seyfert galaxies exhibit distinct emission lines in their spectra-specific wavelengths of light that tell us about the composition and motion of the gas. These lines, both broad and narrow, are indicators of the high-speed motion and density of the surrounding gas, revealing the complex interactions between the supermassive black hole and its immediate environment. The intense radiation pressure from the accretion disk can also propel material away from the black hole at high speeds, sometimes producing powerful astronomical jets, streams of charged particles shooting out into intergalactic space like cosmic spotlights. The dynamics within Seyfert galaxies, including the feeding and feedback processes of the supermassive black hole, exemplify the broader phenomena at play in active galactic nuclei AGN. Studying them offers invaluable insights into the mechanisms of galactic evolution and the behavior of matter in the extreme gravitational fields of supermassive black holes. They are a profound reminder that the quiet, majestic spirals and ellipses we see are often harboring powerful, unseen engines at their very heart, engines that play a crucial role in shaping their cosmic homes. It's a gentle whisper that even in the vast silence of space, there are immense hidden powers at play waiting to be understood. Now let's take a step back and consider the two primary architectural forms that galaxies tend to adopt across the universe. Imagine two grand cosmic cities built with entirely different designs. On one hand, we have the familiar spiral galaxies like our own Milky Way. These magnificent structures flaunt well-defined, disc-shaped forms with graceful luminous spiral arms radiating outwards from a central bulge. Think of a cosmic pinwheel slowly spinning with bright lanes of stars and gas. On the other hand, we have the elliptical galaxies, which lack these distinctive spiral features. Instead, they present themselves as more rounded or elongated spheroids, like cosmic rugby balls, or perfect spheres without any visible spiral arms or a marked disk. The stars within spiral galaxies generally orbit in a relatively ordered flat rotation pattern within their disk, like dancers moving in concentric circles. In contrast, the stars within elliptical galaxies orbit in randomized directions, like bees swarming around a hive, contributing to their overall smooth, three-dimensional shape. This starkly contrasts with the flat organized rotation patterns of stars and gas in spiral galaxies, highlighting their distinct internal dynamics. Elliptical galaxies harbor some unusual properties that set them apart in the cosmic menagerie. One such property is their stellar population. They predominantly contain older, redder stars, giving them a more uniform, often reddish-orange coloration. They are also generally devoid of the cold gas and dust, the very ingredients necessary for new star formation. This characteristic suggests that elliptical galaxies are typically in a more mature or perhaps later evolutionary stage compared to their spiral counterparts. It's as if they have used up all their youthful star-forming energy. Additionally, elliptical galaxies often rank among the most massive galaxies in the universe, with some known as giant ellipticals, containing trillions of stars and spanning across millions of light-years. Despite their massive sizes, they can pack stars in a remarkably dense fashion, particularly towards their centers, where stars are incredibly close to each other, creating a blaze of light. Another intriguing aspect of elliptical galaxies is their formation process. It is widely believed that many elliptical galaxies form as the result of major galaxy mergers. Imagine two grand spiral galaxies, each a bustling cosmic city, gently but inevitably drifting towards each other, their gravitational embrace leading to a slow-motion collision. When two spiral galaxies collide and eventually merge, their abundant gas and dust are either consumed in a frantic burst of star formation, a last glorious hurrah, or they are violently expelled by the forces of the collision, leaving behind a galaxy composed primarily of older stars and with little material left for creating new ones. These colossal collisions can also spur the growth of a galaxy's central supermassive black hole, further quenching star formation by heating and expelling any remaining gases. This transformative and often violent process highlights the dynamic and ever-changing nature of galaxy evolution, showcasing the important role that elliptical galaxies play in deciphering the life cycles of the universe's vast assemblies of stars. They are silent monuments to ancient cosmic battles, their smooth, serene appearance belying a tumultuous past. Now let us turn our eyes to one of the most visually stunning and surprisingly rare cosmic structures found in the universe: ring galaxies. Imagine a celestial jewel, a perfect luminous ring of stars, gas, and dust encircling a relatively empty space where the core of a galaxy would normally reside. This distinct and captivating appearance sets them apart from the more common galactic forms, such as the spirals and ellipticals we just gently explored. They are like a cosmic ripple frozen in time. A fascinating aspect of ring galaxies is that their formation is typically the result of violent cosmic events, the chief among them being the head-on collision of two galaxies. Imagine a smaller, denser galaxy, perhaps a compact dwarf galaxy, or a small spiral acting like a cosmic bullet plunging directly through the very core of a larger disc-shaped galaxy. This is not a gentle graze, but a direct, piercing impact. The process leading to the creation of a ring galaxy is a magnificent slow-motion ballet of gravitational forces. When the smaller galaxy passes through the core of the larger one, it doesn't cause a direct smash of stars because the distances between stars are so vast. Instead, its immense gravitational pull generates a powerful gravitational shock wave that propagates outward from the point of impact, much like a ripple expanding across a pond after a stone is dropped. As this wave moves outwards through the larger galaxy's disk, it sweeps up and compresses the existing gas and dust in its path. This compression, like a cosmic pressure cooker, triggers an intense and rapid period of star formation in a brilliant ring-like structure around the galaxy's center. It's a sudden, glorious burst of new light, creating the luminous ring. As the wave continues its outward journey, it leaves behind a relatively star-poor, empty core, giving the galaxy its characteristic ring appearance. Over time, the newly formed stars in the ring illuminate it, making the galaxy visible across vast cosmic distances. What makes ring galaxies especially intriguing to astronomers is their transient nature. The spectacular ring structure is a temporary phase in the life of a galaxy, lasting only a few 100 million years, a mere flicker in cosmic time before the effects of gravitational forces and the ongoing processes of galactic evolution gradually alter its appearance. Thus, Studying ring galaxies offers a unique opportunity to understand the dynamics of galactic collisions and the specific conditions that lead to such rapid bursts of star formation. They provide invaluable insights into the complex and ever-changing tapestry of the universe, reminding us that even the most beautiful and seemingly stable structures can be fleeting, born of cosmic violence and destined to transform. They are a visual symphony of creation born from chaos, a gentle reminder of the universe's powerful artistry. And now, let us consider a galaxy that exists in a kind of cosmic limbo, a bridge between the elegant spirals and the serene ellipticals. These are lenticular galaxies holding a unique position in the cosmic classification of galaxies, bearing the label of S0 in the traditional Hubble sequence. Imagine a galaxy that has shed its flowing, graceful arms, but still retains a disc-like shape, a central bulge, and a flat, featureless disk. They are like spiral galaxies that have grown old and tired, their star-forming fires having dwindled, leaving behind a smooth, almost ghostly disk. What makes lenticular galaxies unique is their content and structure. They often contain more old stars and significantly less interstellar gas and dust than typical spiral galaxies. This scarcity of raw materials for star formation indicates a much lower rate of current stellar birth. It's as if their star-forming factories have largely shut down. However, unlike the truly three-dimensional elliptical galaxies, lenticulars retain a clear disk shape. This suggests that unlike ellipticals, their formation might not have involved a major violent disruption of their rotational dynamics. The presence of a disk implies that these galaxies could have evolved from spiral galaxies that have somehow lost their gas, perhaps through environmental effects, such as ram pressure stripping in dense galactic clusters. Imagine a galaxy moving through a dense intergalactic medium and the gas within it being stripped away like wind blowing away smoke. This process would prevent the formation of new stars and lead to the fading of spiral arms, eventually leaving behind a lenticular form. Lenticular galaxies are also notable for their diverse environments. They are commonly found in dense regions of the universe, such as the cores of galaxy clusters, where gravitational interactions with other galaxies and the intracluster medium can indeed strip away gas and quench star formation. However, they can also exist in more isolated areas, suggesting that multiple formation pathways might lead to their distinctive appearance. Perhaps some are truly ancient spirals that have simply run out of fuel, while others were stripped clean by environmental forces. The study of lenticular galaxies, therefore, offers valuable insights into the processes that can alter a galaxy's structure and star-forming activity. They are like missing links in the evolutionary chain of galaxies, helping us understand the transitions between different galactic types. By observing these quiet, disc-shaped entities, astronomers can gain a better understanding of how environmental factors and internal processes contribute to the complex life cycles of galaxies, enriching our understanding of the cosmic tapestry. They are a gentle whisper about galactic metamorphosis, a story of subtle transformation over billions of years. And finally, let us turn our attention to the true rebels of the cosmos, the galaxies that refuse to fit neatly into any category. These are the peculiar galaxies standing as the mavericks of the universe, defying the standard classifications of spiral, elliptical, and lenticular galaxies. Imagine an artist's palette filled with vibrant, swirling colors, but then a few splashes and distortions that refuse to be constrained by the canvas's edge. These unique entities captivate astronomers and cosmic enthusiasts alike with their irregular shapes and atypical features which starkly contrast against the more uniform appearance of their conventional counterparts. They are the cosmic oddities, the beautiful aberrations. Peculiar galaxies owe their distinctive characteristics to a variety of dynamic processes and events. Chief among these are galaxy collisions and mergers, where two or more galaxies gravitationally interact, pulling and tearing at each other. Tidal interactions with neighboring galaxies, even without a full collision, can also dramatically distort their structures, much like the moon's gravity pulls at Earth's oceans. And sometimes internal phenomena within the galaxy itself can disrupt its structure, causing it to lose its pristine shape. The unusual features exhibited by peculiar galaxies are as diverse as the processes that create them. Some display highly distorted structures with elongated tidal tails, long stretched-out streams of stars and gas pulled from the galaxy by gravitational forces, sometimes extending for hundreds of thousands of light years. Others might have bridges connecting them to other galaxies, remnants of a close encounter or an ongoing merger. Still others display dramatic rings of gas and stars similar to the ring galaxies we explored earlier, but perhaps less symmetrical or more chaotic. All of these are telltale signs of powerful gravitational interactions or past collisions. Some peculiar galaxies may possess jets of material being ejected from their cores, unusual for galaxies not classified as active galactic nuclei, indicating that their central supermassive black holes might be in an active, but perhaps short-lived state. There are also those that appear to be in the process of merging, showcasing two or more nuclei within a single chaotic envelope of stars and gas, suggesting a future as a unified, though likely irregular, galactic entity. One of the most intriguing aspects of peculiar galaxies is their role as cosmic laboratories. They offer unparalleled opportunities to understand the mechanics of galaxy evolution, interaction, and merger processes in real time. By studying these galaxies, astronomers can gain a better understanding of the life cycle of galaxies, the transfer and transformation of matter in the universe, and the complex gravitational choreography that shapes the cosmic landscape. They are a dynamic, often chaotic canvas that allows us to witness the universe in its most transformative moments. These galaxies not only challenge our understanding, but also profoundly enrich it, revealing the truly dynamic and often bewildering nature of the universe. They are a loud, vibrant whisper, reminding us that beauty can be found even in the most distorted and chaotic forms. As we continue our gentle drift through the cosmic night, having marveled at the diverse forms and tumultuous lives of distant galaxies, let us now turn our gaze a little closer to home, to our own galactic neighborhood. Here we find a grand familiar spiral, our colossal sibling, the Andromeda Galaxy. Imagine her vast and luminous, a celestial island shimmering in the darkness, a mere 2.5 million light-years away. A cosmic stone's throw, relatively speaking. Andromeda, also known as M31, holds a pivotal place in the annals of astronomical study and imagination. She is the nearest large spiral galaxy to our own Milky Way, and here lies one of her most astonishing secrets. She is on a collision course with our galaxy. Imagine two magnificent cosmic dancers, each swirling gracefully in their own space. Slowly, imperceptibly at first, they begin to drift towards each other, drawn by an irresistible gravitational embrace. This impending cosmic event, predicted to culminate in a grand merger in about 4 billion years, provides a fascinating glimpse into the future dynamics of galactic evolution and the ultimate fate of our own home galaxy. It won't be a head-on crash in the way two cars collide. The distances between stars are so vast that individual stars are highly unlikely to smash into each other. Instead, it will be a slow, majestic gravitational dance, a merging and reshuffling of cosmic neighborhoods, eventually forming a new, larger elliptical galaxy. It's a profound thought that our familiar night sky, with its serene Milky Way, is destined for such a dramatic transformation. A quiet reminder that nothing in the universe remains static. One of the more surprising aspects of Andromeda, discovered through meticulous observation, is her massive halo. Imagine a vast, almost invisible sphere of hot gas, and perhaps even darker, more mysterious components, extending about 1.3 million light-years from her center, and possibly as far as 2 million light-years in some directions. This colossal halo is nearly half the distance to our Milky Way, suggesting an impending interaction between the halos of Andromeda and the Milky Way long before the actual galactic cores collide. It's like two giant ethereal clouds slowly beginning to intermingle their outer wisps, a preamble to the grand merger. This halo, far more extensive than previously thought, offers crucial clues about the total mass of the galaxy and how galaxies might accumulate matter over cosmic time. It's a silent, almost ghost-like embrace that has already begun. Another unexpected discovery within Andromeda is the presence of a population of older redder stars that form a giant ring-like structure. This cosmic ring, far fainter and larger than the dramatic rings we might see in a peculiar galaxy, is possibly the result of a collision with another galaxy some 2 billion years ago. Imagine a smaller galaxy, a cosmic intruder, having once pierced through Andromeda's disk, sending ripples through her ancient stellar populations. This event hints at Andromeda's complex and possibly violent past, suggesting that her current graceful spiral structure may be the outcome of numerous past mergers and interactions. It offers tantalizing clues about the ways galaxies grow and evolve over time, not just by accretion of gas, but by absorbing and assimilating smaller neighbors. Their scars subtly written in their stellar distributions. Andromeda also continues to challenge our understanding of galactic formation and behavior with her rate of star formation and the perplexing puzzle of her satellite galaxies. The smaller galaxies orbiting Andromeda, her own miniature celestial entourage, do so in an organized, disk-like structure, a configuration that defies current cosmological models. It suggests a need for deeper insights into the intricate gravitational influences and historical interactions that have shaped the local group of galaxies. Why do these satellites align themselves in such a particular way? Is it a remnant of a larger long-lost structure or a unique dynamical event? These surprises make Andromeda a subject of intense and ongoing study, promising to unravel more cosmic mysteries as our observational technologies and methodologies gently advance. She is not just a neighbor, she is a grand unfolding story, a silent, swirling testament to the dynamic, ever-changing nature of the universe. As we ponder the majestic dance of galaxies, we must now turn our attention to the silent, enigmatic giants that lurk at their very hearts, shaping their destinies in ways both profound and paradoxical. These are the supermassive black holes, the colossal behemoths that reside at the centers of most, if not all, large galaxies. Imagine a universe where every grand city has a hidden powerful engine at its core, an engine that, while invisible, dictates the very pulse and growth of the entire metropolis. Initially, we thought of them as mere byproducts of galactic development, passive heavy anchors in the cosmic sea. But now they are understood to be central players, active architects in the formation and evolution of galaxies. The influence of supermassive black holes on galaxy formation is primarily exerted through a process known as feedback. Imagine the black hole as a cosmic thermostat, regulating the heat and flow of the gas around it. As material spirals into the black hole's immense gravitational embrace, it heats up to incredible temperatures, emitting powerful radiation and often launching powerful jets of energetic particles far out into the galaxy. This energy and material ejected by the black hole interact with the surrounding galactic environment, either igniting new star formation by compressing gas, or more often suppressing it by heating and dispersing the cold gas necessary for stars to form. It's a delicate, powerful balance, a celestial dance between creation and restraint. One of the most unexpected discoveries in this domain is the profound and intimate connection between the mass of a galaxy's central supermassive black hole and the properties of the galaxy's central bulge, the dense central cluster of stars that surrounds the black hole. This suggests a remarkable co-evolution of black holes and galaxies despite their vastly different scales. Imagine a tiny seed growing in perfect proportion to the mighty tree it becomes. This relationship, known as the M-sigma relation, illustrates that the more massive the bulge, the more massive the central black hole. This elegant correlation hints at a powerful feedback mechanism where the black hole, through its energetic outflows and jets, can either remove or heat the galaxy's gas, effectively quenching star formation and limiting the overall size of the galaxy. It's as if the black hole acts as a grand orchestrator, shaping the very growth of its galactic host. Another surprising finding is the dual role of supermassive black holes in fostering star formation in certain conditions. While their energetic jets and intense radiation can and often do suppress star formation by heating and dispersing the cold gas necessary for stars to form, recent observations have shown that in some rare scenarios, these powerful outflows can actually compress gas in more distant parts of the galaxy. Imagine a strong wind, instead of scattering seeds, pushing them together into fertile ground. This compression can trigger the collapse of gas clouds and the subsequent birth of new stars. This intriguing dual role highlights the complex and often counterintuitive influence supermassive black holes have on their host galaxies, capable of both igniting and extinguishing the very processes that lead to galactic growth and evolution. They are not merely cosmic vacuum cleaners, but dynamic integral components that actively shape the cosmos, their invisible presence, guiding the ebb and flow of stellar birth and galactic maturation. These discoveries have significantly altered our understanding of cosmic development, revealing supermassive black holes not as passive relics of a bygone era of galaxy formation, but as dynamic and integral components that actively shape the cosmos. They are a profound whisper in the dark, reminding us that even the most formidable forces can play a role in creation, and that the universe's most majestic structures are often molded by the unseen power at their heart. Now let us imagine a phenomenon of cosmic grandeur, a spectacle that transforms entire island universes. These are galactic collisions, among the most spectacular and transformative events in the universe, playing a pivotal role in the cosmic ballet of galaxy evolution. When galaxies collide and merge, it is not a simple chaotic smash, like billiard balls clashing. Rather, because of the truly vast distances between individual stars within galaxies, these events are more like intricate gravitational dances that can span hundreds of millions, even billions of years. Imagine two immense, shimmering clouds slowly intermingling their constituent particles, rarely touching directly, but rather guiding each other through powerful invisible forces. These cosmic encounters can dramatically alter the structure and composition of the involved galaxies. As their gravitational fields pull at each other, the gas and dust clouds within them are compressed, triggering intense bursts of new star formation. Imagine a sudden glorious blossoming of light across the colliding galaxies as old gas is ignited into new suns. The existing stars are also reorganized, pulled into new orbits and pathways, reshaping the familiar spiral arms or elliptical contours into something new and often peculiar. And crucially, these collisions can funnel vast amounts of gas and dust towards the galactic centers, providing ample fuel for the central supermassive black holes, leading to their ignition or rekindling. One of the most strange and beautiful phenomena resulting from galactic collisions is the creation of ring galaxies, which we briefly touched upon. This rare and exquisite formation occurs when a smaller galaxy punctures directly through the center of a larger disc-shaped galaxy. The impact sends an outward-moving shock wave through the larger galaxy's gas and dust, sweeping it up and compressing it, triggering intense bouts of star formation in a brilliant, expanding ring shape. It's a fleeting, powerful echo of the collision, a cosmic ripple frozen in time. Another intriguing outcome of these gravitational encounters is the formation of tidal tails and streams. Imagine long, delicate, stretched-out ribbons of stars and gas pulled from the galaxies by the powerful gravitational forces during the encounter. These ethereal streams can extend for hundreds of thousands of light years, stretching far into intergalactic space. They can remain visible for billions of years, serving as ghostly cosmic remnants of the galaxy's tumultuous interactions, silent witnesses to a violent past. They are like lingering brushstrokes from a grand cosmic painting, telling a story of past gravitational embraces and tears. Perhaps one of the most significant impacts of galactic collisions is their profound role in the creation of elliptical galaxies. It is widely believed that many of the largest elliptical galaxies, particularly the truly giant ones, form through the merging of two or more spiral galaxies. This grand process can effectively quench star formation within the newly merged entity, either by using up or violently expelling much of the cold gas and dust that would otherwise form new stars. This leads to the characteristic older redder stellar populations, typical of elliptical galaxies, a quiet, stately testament to a long-past violent union. Moreover, these cosmic encounters can funnel vast amounts of gas towards the galaxy's central regions, directly feeding and activating the supermassive black holes residing there. The resulting quasars, or other active galactic nuclei AGN, can outshine entire galaxies and drive powerful winds that influence the evolution of the galaxies long after the initial collision has subsided. It's a powerful feedback loop where the collision fuels the central engine, and the central engine in turn shapes the very destiny of the new merged galaxy. These phenomena highlight the dynamic and ever-changing nature of the universe, where galactic collisions drive the life cycle of galaxies, leading to new structures and configurations influencing star formation and contributing to the complex interplay between galaxies and their central black holes. They are a symphony of chaos and creation, a powerful silent reminder that even destruction can lead to new forms of cosmic beauty. And as we absorb the grandeur of colliding galaxies, let us now step back to the very beginning, to the faint ethereal whisper that carries the story of the universe's birth. This is the Cosmic Microwave Background, CMB, a fundamental piece of evidence for the Big Bang Theory and a true cornerstone of modern cosmology. Imagine the universe itself as a vast ancient parchment, and the CMB as the faint warm glow that still emanates from its earliest lines, a relic of its very first moments. It is the afterglow of the universe's birth, a remnant radiation field that permeates and fills the entire cosmos, providing an astonishing snapshot of the infant universe when it was just about 380,000 years old. To grasp the significance of this, imagine a time when the universe was incredibly hot and dense, a thick, opaque plasma, where light particles, photons, were constantly scattering off free electrons unable to travel freely. It was a cosmic fog, but then as the universe expanded and cooled sufficiently to a temperature of about 3,000 Kelvin, protons and electrons finally combined to form stable, neutral hydrogen atoms. This moment, known as recombination, or the epoch of last scattering, was a profound phase transition. Suddenly, the universe became transparent to light for the very first time, and the photons, no longer constantly scattered, were free to stream across space. These are the photons we now detect as the CMB, having traveled for 13.8 billion years, stretched and cooled by the universe's expansion, reaching us today as faint microwaves a mere few degrees above absolute zero. What truly astonished scientists when they began to study this ancient light was its remarkable uniformity across the sky. Yet, upon closer inspection, they found something even more profound: slight variations in temperature fluctuations of just a few microkelvin. Imagine a perfectly smooth ancient painting, and then, with the most delicate touch, you discover incredibly subtle, almost imperceptible brushstrokes within it. These tiny temperature variations, seemingly insignificant, correspond to the distribution of matter in the early universe. They are the subtle density differences, the tiny ripples in that primordial plasma that eventually acted as the seeds from which all the structures in the universe have grown: the stars, the galaxies, and the grand clusters of galaxies we see today. It's as if the universe's blueprint was subtly etched into this early light, guiding the formation of everything that was to follow. One of the most unexpected and groundbreaking revelations provided by the CMB is the detailed composition and structure of the early universe. Detailed measurements of these subtle fluctuations have allowed scientists to determine the universe's age with astonishing precision: 13.8 billion years. Its geometry, remarkably flat, as we discussed with cosmic inflation, and its composition revealing the surprising dominance of dark matter and dark energy. It's like being able to tell the entire life story of a person just by examining the faint echo of their first breath. Another unexpected finding from studies of the CMB is the confirmation of the existence of acoustic oscillations, sound waves, propagating through the hot, dense plasma of the early universe. Imagine the universe in its infancy, reverberating with cosmic sound. These sound waves left distinct imprints in the CMB, like ripples in a pond that we can still observe today. Studying these patterns offers deep insights into the nature of matter and energy in the universe at that time, and provides further evidence for the accuracy of our cosmological models. Moreover, the CMB has provided compelling evidence for the concept of inflation, the theory suggesting that the universe underwent an incredibly rapid exponential expansion just fractions of a second after the Big Bang. The observed uniformity and flatness of the CMB are elegantly explained by inflation, which stretched out any initial irregularities and smoothed the fabric of spacetime. The CMB continues to be a focus of intense study, with each new observation refining our understanding of the cosmos's origin, evolution, and fundamental nature, making it one of the most powerful and poetic tools in the arsenal of cosmologists. It is a soft, warm echo from the very first moments of everything, a reminder that even the most profound stories begin with a gentle whisper of light. As we gently float through the quiet expanse of the cosmos, having journeyed from the vast, shimmering structures of galaxies to the faint, ancient glow of the cosmic microwave background, let us now turn our attention to the more subtle, yet equally profound ripples and unseen forces that weave through the universe. Imagine a vast invisible scaffolding stretching across billions of light years, providing the underlying structure upon which galaxies are built. This is the realm of dark matter. Halo's theoretical cosmic structures, composed predominantly of dark matter itself, that mysterious invisible form of matter that does not interact with electromagnetic forces. This means it neither emits, absorbs, nor reflects light, making it completely invisible to all our current detection methods, a ghostly presence that we can only infer. These halos are thought to envelop galaxies and galaxy clusters, providing the essential gravitational framework, like an unseen skeleton necessary for the formation and stability of these grand cosmic entities. The very concept of dark matter halos arises from the perplexing observation that galaxies and galaxy clusters exhibit gravitational effects that simply cannot be explained by the visible matter alone. For instance, the outer stars and galaxies rotate at speeds that are far too fast. Without the extra gravitational pull of dark matter, these stars should be flung out into the void like marbles spinning off a fast rotating turntable. Similarly, the immense gravitational lensing we observe around galaxy clusters, where the gravity of the cluster bends the light of more distant galaxies, distorting their images, requires far more mass than we can see. This invisible mass is the dark matter in its halo, gently holding the cosmic structures together. One of the most unexpected properties of dark matter halos is their distribution and sheer size. Unlike the luminous parts of galaxies that we can observe directly, the bright swirling arms of a spiral or the glowing core of an elliptical dark matter, halos extend much, much farther into space. They literally dwarf their visible counterparts in both volume and mass. Imagine a tiny luminous pearl suspended within a colossal invisible cloud that stretches far beyond your sight. This implies that the vast majority of a galaxy's mass is actually located in its dark matter halo, a fact that significantly alters our understanding of galactic structure and mass distribution. It's a profound realization. Everything we see is just the tip of a much larger unseen iceberg, and the visible galaxy is merely a tiny beacon within a much vaster, unseen embrace. Another intriguing aspect is the clumpiness of dark matter halos. Sophisticated simulations of the universe's evolution, born from our understanding of gravity and the Big Bang, suggest that dark matter is not evenly distributed across these halos. Instead, It forms intricate clumps and subtle streams within them, like invisible eddies and currents within a vast, dark ocean. This clumpiness could have profound implications for the formation of galaxies and the distribution of stars within them, subtly influencing everything from a galaxy's overall shape to its very ability to form new stars. It's a reminder that even the invisible has its own complex internal structure, guiding the cosmos in ways we are only just beginning to decipher. Perhaps the most paradoxical feature observed in dark matter halos is what scientists call the core cusp problem. Theoretical models based on our current understanding predict that the density of dark matter should increase sharply towards the very center of the halo, forming a cusp, a dense peak. However, observations of the rotational speeds of stars and gas in the central regions of many galaxies suggest a much flatter density profile at their centers, or even a core where the dark matter is more smoothly distributed. This discrepancy between prediction and observation remains one of the unsolved puzzles in understanding dark matter halos and challenges our current models of cosmic structure formation. It's like discovering that the heart of an invisible giant is not as dense as you expected, forcing us to re-examine our very ideas of its composition. The study of dark matter halos not only offers crucial insights into the elusive nature of dark matter itself, but also into the fundamental processes that govern the formation and evolution of galaxies across the cosmos. They are a silent, invisible testament to the depths of our ignorance and the vastness of what remains to be discovered. Now let us turn our ears to the universe and listen for the faintest whispers, the subtlest echoes of its most violent and magnificent events. These are gravitational waves, ripples in the very fabric of space-time itself. Imagine dropping a heavy stone into a perfectly still pond. The ripples spread outward, carrying information about the disturbance. Gravitational waves are precisely like this, but the pond is space-time, and the disturbances are the most cataclysmic events in the cosmos. The collision of black holes, the spiraling embrace of neutron stars, the final explosive breaths of giant stars. Before their detection, our knowledge of cosmic phenomena like black hole mergers was purely theoretical, elegant predictions of Albert Einstein's general theory of relativity from 1916. For a century, these elusive waves remained a scientific holy grail, a whisper from the cosmos that we long to hear. Then, in 2015, a monumental moment arrived. The Laser Interferometer Gravitational Wave Observatory LIGO, a pair of incredibly sensitive detectors, one in Washington and one in Louisiana, finally heard that whisper. They detected these elusive waves for the very first time, heralding a new era in observational astronomy. This groundbreaking discovery, known as GW-9 was not just a confirmation of Einstein's predictions. It provided the first direct evidence of black holes colliding and merging billions of light-years away. What was particularly surprising about this event was its source, the merger of two black holes with masses about 29 and 36 times that of our Sun, respectively. Prior to this observation, the existence of binary black hole systems, two black holes orbiting each other, was purely theoretical, and many scientists were skeptical about their commonality or even their existence in the first place. The detection not only confirmed that these exotic systems exist, but also that their mergers are powerful enough to produce gravitational waves detectable across such immense cosmic distances, opening a new window into studying such incredibly violent cosmic phenomena. Another surprising aspect was the sheer magnitude of the energy involved in this event. The gravitational wave event released about 3 solar masses worth of energy in mere fractions of a second. Imagine 3 times the mass of our Sun, converted entirely into pure energy, released in less time than it takes to blink. This rate of energy emission is many, many times greater than that of all the stars in the observable universe combined. This astonishing fact showcased the incredible power of gravitational dynamics in the most extreme environments. A silent roar from the depths of space-time, The detection also demonstrated the incredible precision and sensitivity of the LIGO detectors. To capture these waves, the observatories had to measure distances to a fraction of the width of a proton over kilometer-long arms of the interferometers, an engineering feat that was until then unproven at such scale and precision. This sensitivity was surprising and encouraging, suggesting that the nascent field of gravitational wave astronomy would soon grow rich with data from other cataclysmic events across the cosmos. It was like finally building an ear so finely tuned it could hear a pebble drop on a distant world. Lastly, GW145 detection was surprising for its profound implications for fundamental physics and astronomy. It provided a direct test of general relativity under extreme conditions, confirmed the existence and properties of binary black hole systems, and inaugurated the field of gravitational wave astronomy, a completely new way of observing and understanding the universe. Since then, gravitational waves have unveiled the existence of previously unknown black holes, shedding light on their properties and frequencies of collision throughout the cosmos. Even more profoundly, scientists detected waves from a collision between two neutron stars. This event observed not only in gravitational waves, but also across the entire electromagnetic spectrum. In gamma rays, X-rays, and visible light opened the door to multi-messenger astronomy. It offered unprecedented insights into how heavy elements like gold and platinum are forged in the cataclysmic aftermath of neutron star mergers, a mystery that had puzzled scientists for decades. Through gravitational waves, we are gently peeling back layers of the universe, revealing the secrets of its most extreme events in a way that was once considered pure science fiction, a silent, powerful song reaching across the cosmos. As we continue to listen to the universe's most extreme echoes, let us now turn our attention to the most luminous and violent electromagnetic events, bursts of energy so powerful they defy easy comprehension. These are gamma ray bursts, GRBs, intense flashes of gamma rays that can last from a few milliseconds to several hours, yet release as much energy in a few seconds as the sun will in its entire 10 billion year lifetime. Imagine a sudden blinding flash from across the cosmos, a light so fierce it would overwhelm countless galaxies. Initially detected in the late 1960s by satellites designed to monitor nuclear weapons tests on Earth, a surprising and almost ironic beginning for a cosmic discovery. These enigmatic phenomena remained a profound puzzle for decades. Scientists have since identified two primary types, each with its own dramatic origin story. Short-duration bursts, typically lasting less than 2 seconds, are believed to originate from the mergers of neutron stars, or a neutron star and a black hole. Imagine two incredibly dense, spinning remnants of dead stars spiraling closer and closer, eventually colliding in a spectacular burst of light and gravitational waves. Long-duration bursts, which last more than 2 seconds, are associated with the supernova explosions of massive stars, the final glorious collapse of a truly giant sun. One unexpected source of gamma-ray bursts was identified when astronomers observed a short-duration burst emanating from a galaxy billions of light-years away that appeared to lack the dense, star-forming regions where neutron star mergers were presumed to primarily occur. This finding was a gentle surprise, suggesting that the mechanisms and environments capable of producing gamma-ray bursts might be much more diverse and widespread than previously thought. It's as if you expected fireworks only from a grand stadium, but then saw them erupt from a quiet, unexpected clearing in the distance. Additionally, in 2013, an extremely bright and long-lasting gamma-ray burst challenged our understanding by suggesting a possible connection between certain bursts and the formation of magnetars, those incredibly powerful, highly magnetic neutron stars we discussed earlier. This event hinted at the idea that not all long-duration gamma-ray bursts might be exclusively tied to supernovae, opening new avenues of research into the life cycles of stars and the extreme conditions under which these titanic explosions are produced. It's a whisper that the universe's stories of stellar death are far more varied and complex than we had imagined. These enigmatic flashes continue to intrigue astronomers, offering a glimpse into the most energetic and violent processes in the universe. They serve as cosmic lighthouses, their brilliant, fleeting light traveling across immense distances, allowing us to probe the early universe and understand the extreme physics at play. The sheer energy levels and the varying frequencies at which these bursts occur have made understanding their physical mechanisms a compelling puzzle. The intrigue surrounding GRBs has made them one of the biggest mysteries in astronomy, because solving their origins could provide profound insights into the universe's properties, the behavior of matter under the most extreme conditions, and perhaps even unlock new physics that could explain their incredible power. They are a loud, fleeting testament to the raw, untamed power of the cosmos, reminding us that even in the vast silence, there are moments of unimaginable brilliance. Now let us turn our attention to the serene, distant outskirts of our own cosmic home, a place of quiet mystery that has never been directly seen. Yet its presence is powerfully felt. This is the Oort cloud, a theorized vast spherical shell of icy objects that gently envelops our solar system. Imagine our sun and its planets as a tiny luminous pearl, and the Oort cloud as the soft, immense, and almost invisible cotton ball that surrounds it, stretching far beyond the orbits of even the most distant planets like Neptune and Pluto. Its immense size is hard to grasp. It lies at distances ranging from a staggering $5,000 to 100,000 astronomical units from the Sun, an astronomical unit being the distance from the Earth to the Sun. To put that in perspective, the Oort cloud could be as far as a quarter of the way to the nearest star. This incredibly distant region is believed to be the source of long-period comets, those majestic celestial wanderers that grace our skies only once every few centuries, their tails stretching across the heavens. These comets provide a tangible, albeit infrequent, connection between us and this remote, mysterious frontier of our solar system, like messengers from the deep, dark outer reaches. Despite its pivotal role in the genesis of comets, the Oort cloud remains one of the solar system's most enigmatic features, primarily because it has never been directly observed. Its existence is inferred from the behavior and origins of these long-period comets, from careful mathematical models, and from the subtle gravitational influence of the Sun and nearby stars over eons. It's like knowing a vast, unseen forest exists, because you occasionally see a few leaves drifting from its edge. One of the greatest mysteries surrounding the Oort cloud concerns its formation and evolution. Scientists theorize that it is made up of material left over from the formation of the solar system itself, icy planetesimals, that were initially much closer to the Sun, but then they were ejected to its outermost reaches by the powerful gravitational forces of the young giant planets Jupiter, Saturn, Uranus, and Neptune, as these planets migrated and settled into their orbits. Yet, how these billions of icy objects survived the solar system's tumultuous early history, and precisely how the cloud was shaped into its vast spherical form, are questions that remain open, whispered uncertainties in the dark. Another intriguing puzzle is the influence of galactic tides and passing stars on the Oort cloud. Our solar system is not isolated. It is gently, imperceptibly orbiting within the vast disk of the Milky Way galaxy. The gravitational pull of the galaxy's overall mass distribution, known as galactic tides, combined with the occasional close flyby of other stars, are thought to subtly tug at the Oort cloud. These gentle tugs can occasionally dislodge a comet from its icy haven, sending it on a long, slow journey towards the inner solar system, where it finally warms and sprouts its magnificent tail. But the specifics of these interactions and their implications for the cloud's structure and stability are not fully understood. The potential discovery of Planet 9, a hypothetical planet believed to be influencing the orbits of distant objects in the solar system beyond Neptune, adds another layer of mystery. If it exists, Planet 9 could provide insights into the cloud's outer limits and the dynamics of our solar system's true frontier. The Oort cloud symbolizes the frontier of human curiosity, an astronomical phenomenon that hints at the vastness of our solar system and challenges our understanding of how it came to be. It's a silent, almost mythical place, a reservoir of ancient ice and profound questions waiting for us to one day peer into its depths and unlock its secrets, revealing new truths about the origins of our cosmic neighborhood. As we continue our gentle contemplative journey through the vast, dark ocean of space, let us now turn our gaze to another region of quiet mystery, a place that stretches just beyond the familiar planets of our solar system. This is the Kuiper Belt, a vast donut-shaped area of space that lies beyond the orbit of Neptune, extending from about 30 to 50 astronomical units from the Sun. Imagine our Sun and its inner planets as a luminous central core, and the Kuiper Belt as a distant, sprawling cosmic freezer filled with icy bodies, dwarf planets, and countless comets. It represents the pristine remnants from the early solar system's formation over 4 billion years ago, a time capsule preserving the very building blocks of planets and offering us a precious glimpse into our solar system's distant past, undisturbed and frozen in time. The Kuiper Belt is far more than just a collection of cosmic debris. It is a vast reservoir of icy small worlds, a place where the sun's light is dim and its warmth barely reaches. These icy bodies are like silent sentinels, holding clues about the conditions and materials present in the outer solar system. During its tumultuous youth, they are composed primarily of ices, water ice methane, ice ammonia, ice, along with rocky materials, much like the comets that occasionally visit the inner solar system. One of the most significant and unexpected discoveries within the Kuiper Belt was the dwarf planet Eris in 2005. Its discovery was particularly startling because initial observations suggested it appeared to be slightly larger than Pluto. This seemingly small fact sparked a profound debate and ultimately challenged long-standing notions of what truly constituted a planet, culminating in the reclassification of Pluto as a dwarf planet in 2006 by the International Astronomical Union. This decision, though controversial for some, brought significant attention to the Kuiper Belt and its inhabitants, revealing that our solar system's outer reaches were far more populated and dynamically complex than previously imagined. It was a gentle shake to our understanding, reminding us that definitions, even cosmic ones, are not set in stone. Further exploration of the Kuiper Belt has revealed a captivating variety of other unexpected objects, each with its own unique story. We've discovered Haumea, a dwarf planet with a mysterious elongated shape spinning so rapidly it's flattened like a cosmic football, and surprisingly even a ring system, an unusual feature for an object in the Kuiper Belt. Imagine a distant egg-shaped world adorned with a delicate ring, a true cosmic anomaly. Then there's Makemake, another dwarf planet found to have an extremely bright surface covered with methane ice, showing just how diverse the conditions and compositions can be on these distant frozen bodies. These findings hint at a rich tapestry of geochemical processes occurring even in the deepest, coldest corners of our solar system. Perhaps one of the most intriguing finds was the discovery of Sedna, a distant object with an extraordinarily long and elongated orbit that takes it far beyond the main Kuiper Belt to the very outer edges of the solar system. Sedna's peculiar orbit suggests the possible presence of more unseen worlds, or even the hypothetical Planet 9, a giant world whose gravitational influence could be subtly shaping the orbits of these distant objects. This whisper of another much larger unseen planetary body lurking in the farthest reaches of our solar system adds another layer of profound mystery to the Kuiper Belt. The Kuiper Belt continues to intrigue astronomers with its diverse collection of icy bodies, each discovery peeling back another layer of our solar system's early history and evolution. These unexpected findings challenge our understanding and prompt further exploration, hoping to answer fundamental questions about the composition of these distant objects and the ancient processes that shaped them. It's a silent cosmic archive, slowly patiently revealing the story of our solar system's birth and youthful chaos. A story written in ice and rock, waiting for us to read its quiet pages. Now let us turn our minds to a phenomenon of incredible scale, a mysterious force that tugs at entire galaxies, pulling them towards an unseen point in the vastness of space. This is the Great Attractor, a gravitational anomaly located in the vicinity of the Hydra Centaurus supercluster, roughly 150 to 250 million light-years away from our own Milky Way. Imagine a vast invisible whirlpool in the cosmic ocean, subtly yet powerfully drawing everything towards its unseen center. It represents a point in the universe towards which our Milky Way and hundreds of thousands of other galaxies are moving with a collective velocity of about 600 kilometers per second, an astonishing speed even on cosmic scales. This massive flow of galaxies, observed through their redshifts, the stretching of light waves as objects move away from us, indicates the powerful presence of something incredibly massive exerting a gravitational pull on an intergalactic scale. Yet precisely what constitutes this great attractor has long puzzled astronomers. One of the main reasons its gravitational pull is considered so mysterious hinges on the difficulty of directly observing it. The zone of the Great Attractor lies in a direction heavily obscured by the Milky Way's own thick disk, a region densely packed with stars' dust and gas that absorb and scatter light. Imagine trying to see a distant object through a dense, swirling fog. This area of intense obscuration has earned it the apt title of being part of the zone of avoidance. Despite our most powerful optical telescopes, this cosmic veil makes it incredibly hard to peer through and study the region in detail, leaving its true nature shrouded in mystery. Despite these significant observational challenges, advances in specialized astronomy using X-ray, infrared, and radio wavelengths, which can penetrate much of the obscuring dust and gas, have allowed researchers to begin to pierce through this veil. What they have revealed is an incredible scene, a dense concentration of clusters and superclusters of galaxies. This region contains significantly more matter than expected, including a substantial amount of dark matter, which, as we gently learned, does not emit or absorb light, but powerfully reveals its presence through its gravitational effects. The Great Attractor itself appears to be a gravitational focal point within the larger Laniakea supercluster, a truly vast network of galaxies to which our Milky Way also belongs. It's as if we are part of a giant river system, and the Great Attractor is the unseen powerful current that subtly directs the flow of countless galactic streams. The mysterious nature of the Great Attractor also stems from our still incomplete understanding of the distribution and behavior of dark matter and the grand dynamics of superclusters. Despite its immense gravitational influence, the detailed composition and the full scope of the Great Attractor remain subjects of intense ongoing study. It's a profound whisper from the deep structure of the universe, promising to shed light on the grand architecture and evolution of our local corner of the universe and the dark, unseen underpinnings of cosmic infrastructure. It's a silent, powerful tug, reminding us that even the largest structures are part of a grander, unseen cosmic dance, and that much remains hidden, waiting for us to patiently listen and learn. Let us now gently descend from the vast, unseen currents of galactic flows and focus on a much more intimate, yet equally profound secret held by our closest planetary neighbor. For decades, Mars has been depicted in our stories and early scientific imaginings as a barren, dry, cold world, a vast red desert. But recent missions with their intrepid rovers and orbiting eyes have painted a far more complex and surprising picture, revealing its watery history, and even more astonishingly, hints of water in its present condition. Imagine looking at an old faded photograph of a bustling city, then discovering that beneath the dusty image there are faint, shimmering outlines of rivers that flow even now. One of the most unexpected and truly groundbreaking findings came from the Mars Reconnaissance Orbiter (MRO) and Mars Express missions, which provided strong evidence of liquid water flowing intermittently on Mars's surface in contemporary times. These observations showed dark streaks affectionately known as recurring slope linea RSL appearing seasonally on Martian slopes. These streaks would lengthen and darken during warmer months and fade in cooler ones, strongly suggesting the presence of briny liquid water flowing just beneath the surface. This was a revolutionary discovery, as it indicated that liquid water, albeit in a very salty state, which lowers its freezing point, allowing it to remain liquid in colder conditions, could still exist on Mars's surface today, directly contrary to the long-standing belief that Mars's surface conditions were far too cold and its atmosphere too thin for liquid water to persist. It's a quiet, shimmering whisper of a possibility, a reminder that life might adapt to far more extreme conditions than we once imagined. Another surprising discovery was made by the Phoenix lander in 2008, which detected water ice near the Martian North Pole. The lander's robotic arm scraped away a thin layer of soil, revealing bright material underneath. Over the course of a few days, this bright material sublimated it turned directly from solid to gas, just like dry ice does on Earth, confirming it to be water ice. This finding was pivotal because it demonstrated that water ice exists close to the surface outside of Mars's polar ice caps, suggesting that water ice might be much more widespread and accessible than previously thought, perhaps just a few centimeters beneath the dust in many regions. It was like finding hidden pockets of frozen treasure easily within reach. The Curiosity rover's findings in Gale Crater further challenged our understanding of Mars's watery past. Curiosity discovered ancient streambeds, clear evidence of flowing water from billions of years ago. It found sedimentary layers and mineral deposits that typically form in the presence of water, strongly indicating that Gale Crater once hosted a lake, not just any lake, but a lake with fresh water, a potentially habitable environment for microbial life billions of years ago. This nuanced our view of past Martian environments, suggesting they could have been far more Earth-like and hospitable than the freezing desert-like landscape we see today, a profound whisper of a lush, ancient past. Perhaps most intriguing, a recent finding suggested the presence of a subsurface lake beneath the South Polar ice cap, as well as several smaller bodies of water around it, detected by radar data from the Mars Express orbiter. If confirmed, these could represent the first known stable bodies of liquid water on Mars, raising profound questions about the planet's climatic history and its potential to harbor life in these hidden subterranean realms, protected from the harsh surface conditions. These unexpected discoveries about water on Mars have fundamentally shifted the narrative of Mars from a dry, uninhabitable planet to one with a dynamic history of water flow and retention. Each new finding not only deepens our curiosity and intrigue about our neighboring planet, but also significantly improves our understanding of where life might be found beyond Earth and how planets change over time. It's a gentle, persistent whisper from the red planet, urging us to continue our patient search for its secrets, and perhaps for life itself. As we drift deeper into the mysteries of our solar system, beyond the familiar orbits of our home planets, we sometimes encounter something truly alien, a visitor from another star. Imagine a solitary ship sailing quietly into our familiar harbor, but built of materials and carrying an energy that whispers of origins far, far away. This is the realm of interstellar visitors, celestial objects that wander through the vast darkness between the stars, untethered to any single sun. One of the most famous of these unexpected guests was Oumuamua, an elongated cigar-shaped object that captured our attention in 2017. It was not just for its peculiar motion, but for the profound mysteries it carried from beyond our very own solar system. Oumuamua's significance lies not only in its exotic origin, but in the deep questions it raises. unlike any comet or asteroid we had ever seen before. Oumuamua's high speed and its trajectory unequivocally confirmed its origins lay far beyond our own cosmic neighborhood. It wasn't gravitationally bound to our sun. It was just passing through, accelerating away after a brief, bewildering visit. This meant it had to have come from another star system entirely, perhaps ejected during the chaotic formation of its own planets, a cosmic refugee drifting through the galaxy for eons before stumbling into our path. Its very existence whispers of other solar systems, other cosmic nurseries, and hints at the untold numbers of such wanderers drifting through the vastness. Scientists were particularly puzzled by Oumuamua's unusual acceleration as it passed through our solar system. Its path wasn't entirely explainable by gravity alone. Normally, comets exhibit non-gravitational acceleration due to outgassing. As they approach the sun, their ices heat up and turn into gas, creating small jets that push them slightly off course. However, Oumuamua showed no signs of a comet's tail or any detectable outgassing. This silent, inexplicable push without the telltale sign of a gaseous plume left astronomers scratching their heads. It invited speculation about the object's composition and the nature of interstellar objects. Perhaps it was made of exotic ices that outgassed differently, or perhaps it was something entirely new, something our current understanding couldn't quite grasp. This unusual behavior, coupled with its elongated, almost needle-like shape, suggested by its fluctuating brightness, made Oumuamua a truly enigmatic visitor. Was it a chunk of rock, an icy shard, or something else entirely, something that whispered of processes beyond our current understanding? This silent, puzzling acceleration invites speculation about the nature of interstellar objects and their role in the cosmic ballet, making Oumuamua a harbinger of discoveries that challenge our understanding of the universe's deeper mysteries. It was a fleeting, silent visitor, leaving behind not just questions about its own nature, but profound queries about the existence of other solar systems, the composition of interstellar objects, and the potential for life elsewhere in the universe. Its brief, bewildering visit was a gentle yet powerful reminder that our solar system is not an isolated island, but part of a much larger, endlessly fascinating interstellar ocean, and that strange, beautiful secrets can drift into our view from the deepest, most unexpected currents. As we gently float through the quiet expanse of the cosmos, having encountered unexpected visitors and the hidden depths of our own solar system, let us now turn our minds to a profound journey back in time to the very dawn of the universe. Imagine a time when the cosmos was truly dark, before any stars had ignited a vast, neutral sea of hydrogen and helium. And then a whisper of light appears, the very first stars shattering the darkness. The quest to understand the formation of the first galaxies takes astronomers on a journey back over 13 billion years in cosmic history. Leveraging the universe itself as a kind of time machine, astronomers employ the world's most powerful telescopes, like the Hubble Space Telescope and its successor, the magnificent James Webb Space Telescope, to capture light that has been traveling towards us for billions of years. This ancient light serves as a beacon from the distant past, revealing information about the state of the universe when those photons began their long, arduous voyage across space. By observing these incredibly distant galaxies, we are essentially looking back in time, seeing these objects not as they are today, but as they were when the universe was incredibly young, still taking its first breaths. One truly surprising discovery in this field is the existence of massive galaxies that formed much earlier than current theories of galaxy formation would suggest. Imagine our models predicting that a grand cosmic city should take billions of years to grow to a certain size, yet we find fully formed metropolises in an era when the universe was barely a toddler. Some of these galactic behemoths came into being when the universe was less than 1 billion years old, a period affectionately known as the Cosmic Dawn. Their sheer size and maturity at such an early stage in the universe's history challenge our understanding of how quickly galaxies can form and evolve. It suggests that the processes driving galaxy formation were far more efficient and perhaps even different from what we initially believed. Were there more abundant seeds for growth? Did dark matter halos form faster? These are the silent grand questions whispered by these ancient giants. Additionally, the detection of complex organic molecules in these early galaxies hints at an even more profound possibility. Organic molecules are the very building blocks of life as we know it, the intricate carbon-based compounds that form amino acids, proteins, and DNA. Finding these molecules in galaxies that existed so incredibly early in cosmic history suggests that the fundamental ingredients for life were present much, much earlier than previously thought. This opens new avenues of inquiry into the very origins of life in the universe. It's a gentle, hopeful whisper that the conditions for life might have been brewing across the cosmos almost from the very beginning, a powerful testament to the universe's innate potential for complexity. These observations from the cosmic dawn not only push the boundaries of our understanding of galaxy formation, but also deepen our appreciation for the universe's intricate and surprising evolution. It's a humbling thought that the very first light, having traveled for eons, is now teaching us about the universe's earliest, most fundamental moments. A silent, ancient story unfolding before our very eyes. Now let us imagine the universe taking its first breath of light, emerging from a period of profound darkness. Before the first galaxies could form, the very first stars had to ignite, acting as cosmic pioneers. The discovery of the universe's first stars, often referred to as population 3 stars, brought with it a host of surprises that challenged prior astronomical theories. Imagine the universe as a vast, dark canvas waiting to be illuminated, and then a billion tiny, impossibly bright points of light flicker into existence, pushing back the gloom. One of the most striking revelations was their sheer size and luminosity. These primordial stars were not only believed to be much larger than our Sun, some theorized to be hundreds of times more massive, but also significantly brighter, emitting intense ultraviolet light. This characteristic was unexpected, because in the modern universe, stars of such immense mass are exceedingly rare. Their existence in the nascent cosmos hinted at a very different process of star formation in the early universe, where conditions were ripe for the birth of true giants, unlike anything we commonly see today. It's a whisper of a time when everything was larger, grander, and more extreme. Another surprising aspect was the composition of these first stars. Born from the primordial gas left over from the Big Bang, they comprised almost exclusively of the lightest elements, hydrogen and helium. Crucially, they contained virtually no heavier elements, what astronomers call metals. Imagine a universe with only 2 colors in its palette. This lack of metals meant that the first stars were fundamentally very different from stars formed later in the universe's history, including our own Sun, which contains a mix of heavier elements essential for the formation of planets and life as we know it. These were pristine, pure stars, burning with the original breath of the cosmos, untainted by the complex chemistry that came later. Perhaps the most tantalizing surprise was the role these first stars played in the transformation of the early universe, a pivotal period known as cosmic ionization. Imagine the universe after the initial Big Bang and recombination, being filled with a neutral, opaque fog of hydrogen gas. The universe was dark, as light could not travel freely. But the intense ultraviolet light from these first massive and incredibly luminous stars is believed to have played a critical role in ionizing this neutral hydrogen gas, stripping electrons from their atoms. This process gradually made the universe transparent to light for the first time, marking the end of the cosmic dark ages. It was like the sun breaking through a dense fog, allowing light to flood the landscape. This reionization laid down the foundation for the formation of the structures we see today: galaxies, stars, and eventually the very conditions necessary for life as we know it. The study of the universe's first stars not only provides profound insights into our cosmic origins, but also challenges our understanding of the fundamental processes that shaped the universe. They are the silent, brilliant architects of light, a gentle whisper from the first moments of cosmic illumination, teaching us about the very origins of cosmic structure and the light that guides our universe. From the first glimmerings of light in the early universe, let us now turn to their incredibly bright yet ancient beacons, the ancient quasars. These serve as lighthouses in the vast darkness of the early universe, illuminating our understanding of cosmic history in profound ways. Imagine these quasars as incredibly distant, powerful searchlights, their beams cutting across billions of light years, allowing us to glimpse the universe as it was in its infancy. Quasars, or quasi-stellar objects, are exceptionally bright and energetic centers of young galaxies, powered by supermassive black holes. By studying these cosmic beacons, which date back to a time when the universe was merely a fraction of its current age, astronomers have been able to piece together crucial insights into the rapid growth of black holes, the tumultuous formation of galaxies, and the overall evolution of the universe itself. One unexpected property of these ancient quasars is the sheer size and mass of the black holes at their centers. Imagine finding fully grown ancient trees in a sapling forest. Some of these black holes are billions of times more massive than our sun, raising intriguing questions about how they could have grown so large in the relatively short time since the Big Bang. This profound observation challenges our understanding of black hole growth rates and the dynamics of early galaxy formation. Were there more abundant seeds for these giant black holes? Did they grow by accreting gas at incredibly high rates? Or did they merge with other black holes more frequently in the early denser universe? These are the silent questions whispered by these colossal ancient engines. Moreover, the environments around these ancient quasars have revealed surprises as well. Observations show that these regions of the early universe were already rich in heavy elements, like carbon and oxygen. These are elements that are forged in the fiery interiors of stars and scattered across the cosmos by supernova explosions. The presence of these metals, so early in cosmic history, indicates that star formation and galactic chemical enrichment processes were already well underway, suggesting a universe that was evolving rapidly, even at these earliest epochs. It's a gentle whisper that the cosmic kitchen was already busy cooking up the ingredients for planets and life far earlier than we might have expected. Another intriguing discovery is the detection of large amounts of cool dense gas and dust in the vicinity of some ancient quasars. This provides the raw material for intense star formation, indicating that the host galaxies of these quasars were sites of frenetic stellar birth. This contradicts earlier theories that such energetic phenomena with their powerful jets and radiation would quench star formation by heating and dispersing the gas. Instead, it seems that in some cases the very activity of the black hole might have helped concentrate the gas, triggering new bursts of star formation. Together, these unexpected properties of ancient quasars have significantly deepened our understanding of the early universe, revealing a complex and dynamic cosmos that was evolving rapidly from its infancy. They challenge existing models and push the boundaries of our knowledge, driving the quest for a more refined understanding of the cosmic dawn. They are the luminous ancient voices of the universe, telling us stories of a time when everything was just beginning and the pace of change was breathtaking. Now let us return to the enigmatic architects of these ancient quasars, the very first black holes. The discovery of the first black holes in the early universe marked a pivotal moment in astrophysics, radically transforming our understanding of cosmic evolution. Imagine finding fully formed grand structures in a landscape that was just beginning to take shape. These primordial black holes, found to exist when the universe was less than 1 billion years old, posed a profound challenge to existing theories about the formation and growth of black holes. Significantly, Their mere existence at such early times suggested that black holes could form and grow to immense sizes much more quickly than scientists had previously believed possible. One notable aspect of these early black holes is their mass. Many of them were identified as supermassive black holes containing millions to billions of times the mass of the Sun, situated at the centers of young, still-forming galaxies. The conventional wisdom had been that black holes grew gradually from smaller seeds, slowly accumulating mass over billions of years through the accretion of gas and the merging with other black holes. However, the discovery of supermassive black holes in the early universe implied a different, more rapid origin. They either formed large to begin with, perhaps from the direct collapse of massive gas clouds without forming stars first, or from the early merger of numerous stellar mass black holes, or they grew at rates much faster than any mechanisms known at the time could comfortably account for. It's a silent cosmic puzzle. How did these giants come to be so quickly? Moreover, these ancient black holes provided a unique window into the conditions of the early universe. They offer insights into the formation of the very first stars and galaxies, and even the distribution of dark matter. Their profound influence on their surroundings through processes such as quasar activity. The brilliant light generated as they consume matter and jet emissions. Powerful streams of particles shot out into space played a critical role in shaping the galaxies in which they resided. They were not passive inhabitants, but active sculptors, steering the evolution of the universe by regulating star formation and reionizing the intergalactic medium, clearing the cosmic fog. The unexpected discovery of early universe black holes thus has vast implications, not only for theories of black hole formation and growth, but also for our understanding of cosmological evolution as a whole. By pushing the boundaries of what was thought possible, these findings have inspired new theoretical developments and motivated ongoing observations with the latest generation of telescopes, like the James Webb Space Telescope, which is specifically designed to peer back into these early times. They are a profound whisper from the very beginning of cosmic structure, driving forward the quiet quest to unravel the mysteries of our universe and how its grandest structures came to be. Now let us gently explore the very first chemical ingredients of the universe, the elements that formed in the immediate aftermath of the Big Bang, and those forged in the hearts of the first stars. The study of the formation of elements in the early universe, a field known as nucleosynthesis, employs both meticulous observational astronomy and intricate theoretical physics to unravel how the first elements came to exist. Imagine the universe as a vast primordial crucible, and these elements as the very first ingredients cooked up within it. This fascinating journey begins mere minutes after the universe's birth, when it had cooled sufficiently for protons and neutrons to combine into the simplest nuclei, hydrogen, helium, and mere traces of lithium. This process is known as Big Bang nucleosynthesis, BBN. It was a fleeting, intensely hot moment where the fundamental building blocks of matter assembled into the very first atomic nuclei. The precise amounts of these light elements predicted by BBN models remarkably match what we observe in the oldest, most pristine parts of the universe, a beautiful confirmation of the Big Bang theory itself. However, the further creation of heavier elements, everything from carbon and oxygen essential for life to iron, gold, and uranium, awaited the birth and death of the first stars. Imagine stars as cosmic alchemists, tirelessly transforming lighter elements into heavier ones within their fiery hearts. Astronomers study the elemental composition of ancient stars and distant galaxies by analyzing their light spectra, which contain distinct chemical signatures for different elements. Meanwhile, sophisticated theoretical models of stellar evolution and supernova explosions help predict precisely how elements are forged in the extreme conditions within stars and during their cataclysmic end stages. One unexpected finding from these studies was the discovery of very old stars with extremely low metal content, known as population 2 stars. These are the universe's true elder stars, formed before the cosmos was heavily enriched with heavier elements. They provided a direct link to understanding the universe's initial composition, pristine and almost untouched by later stellar generations. Surprisingly, some of these stars have been found to contain higher than expected amounts of certain heavy elements, suggesting that the processes contributing to nucleosynthesis were more complex and varied than simple models predicted. It's a gentle whisper that the early universe was more chemically intricate than we initially thought, with perhaps a wider variety of early stellar processes at play. Moreover, the detection of certain elements like beryllium and boron, which are not produced in significant amounts in the Big Bang or within stars, indicated the crucial role of cosmic rays in forming elements. These high-energy particles crashing into heavier nuclei can break them apart in a process known as spallation, creating these lighter elements. It's a silent, powerful reminder that even energetic particles from space play a role in the cosmic chemistry. Another unexpected finding has been the stunning observation of heavy elements such as gold and platinum in the aftermath of neutron star collisions. This was a truly profound discovery. It not only revealed a previously unknown site of nuclear synthesis, but also provided a direct way to witness the formation of these most massive and precious elements. It strongly supported the theory that the heaviest elements are formed not just in supernovae, but primarily in the most extreme energetic environments imaginable, the collision of two incredibly dense stellar remnants. It's a whisper that the gold in our jewelry and the platinum in our technology were forged in a violent, distant cosmic embrace billions of years ago. These discoveries have refined our understanding of the universe's elemental abundance and distribution, highlighting the sophisticated interplay between different astrophysical processes and underlining the fact that the universe's early days were far more complex and dynamic than once thought. They are a gentle scientific lullaby, telling us the story of how everything we are made of, every atom in our bodies, was forged in the fiery heart of stars or the cataclysmic aftermath of their deaths, truly making us stardust. As we reach the gentle close of our cosmic journey, having traversed the vast landscapes of galaxies and peered into the fiery hearts of ancient stars, let us now turn our gaze to the horizon of discovery itself, to the tools, the missions, and the profound questions that await us in the future. Imagine looking out from a quiet shore, seeing not just the vast ocean, but the faint glimmer of lights in the far distance, hinting at new lands yet to be explored. This is where we stand now, poised for the next great revelations. Among the most eagerly anticipated of these new eyes on the universe is the James Webb Space Telescope, JWST, hailed as the premier observatory of the next decade and a true successor to the beloved Hubble. Imagine a giant golden origami flower unfolding in the cold vacuum of space, its delicate segments meticulously aligning to form a mirror so large and so sensitive it can capture the faintest whispers of light from across the cosmos. The JWST carries a suite of ambitious goals designed to deepen our understanding of the universe in ways previously unimaginable. One of its primary objectives is to unravel the mysteries of the early universe. By capturing the incredibly stretched and reddened light from the first galaxies that formed shortly after the Big Bang, the JWST will allow astronomers to study the formation and evolution of galaxies over cosmic time with unprecedented detail. It's like having a perfect, clear window into the universe's baby photos, revealing new insights about its earliest history and how the grand structures we see today first began to coalesce from the primordial gas. What secrets do those ancient faint lights hold? The JWST is designed to whisper them to us. Another major goal is to explore the life cycle of stars, from their birth in dense, cold molecular clouds to their ultimate demise as supernovae, or the formation of exotic remnants, like neutron stars and black holes. By observing these processes in unparalleled detail, cutting through the obscuring dust that hides these stellar nurseries, the JWST will provide new data about the complexities of stellar evolution and the cosmic recycling of elements. It will show us how new stars are born, how they live their fiery lives, and how they enrich the universe with the very building blocks of planets and life, a continuous cycle of creation and return. Perhaps most excitingly for many, the JWST is also poised to revolutionize the field of exoplanet research. With its highly sensitive infrared instruments, it will be able to analyze the atmospheres of exoplanets in exquisite detail, identifying the chemical signatures of potential biomarkers, gases like methane, oxygen, or water vapor that could hint at the presence of biological processes. It's like being able to smell the faint scent of life from across unimaginable distances. This could lead to groundbreaking discoveries in our quest to understand if we are truly alone in the universe, shifting the question from, is there life, to, where is it, and what does it look like? As for unexpected discoveries, the JWST's advanced capabilities might uncover phenomena that fundamentally challenge our current understanding of physics and cosmology. Imagine a telescope so powerful, it reveals something utterly new, something that our current theories simply cannot explain. For instance, it could detect previously unknown types of astronomical objects or reveal unexpected patterns in the distribution of matter in the early universe, perhaps even providing new insights into the nature of dark matter and dark energy, or showing us the first signs of truly exotic physics at play. The JWST's exploration of the cosmic unknown promises to open new frontiers in our comprehension of the universe, potentially reshaping our scientific paradigms based on the unforeseen wonders it is bound to discover. It is our generation's grand adventure, a silent, hopeful gaze into the deepest, oldest secrets of the cosmos. Following the JWST, another giant eye is preparing to open, promising to revolutionize our view of the universe from a different vantage point. This is the extremely large telescope ELT, set to become the world's largest optical telescope upon its completion in the Atacama Desert of Chile. Imagine a colossal shimmering eye, nearly 39 meters across, gathering more light than any other optical telescope before it. With this unprecedented size and technological advancements, the ELT will allow astronomers to peer deeper into space with incredible detail. Much like being able to read the smallest print on a page from across a vast hall, one of the paramount objectives of the ELT is to directly image planets orbiting stars beyond our solar system. While the transit method glimpses a planet's shadow and the JWST can analyze atmospheric composition from transits, the ELT aims to actually see these exoplanets as tiny points of light separated from the glare of their host stars. This incredible capability will enable scientists to analyze the atmospheres of these exoplanets in even greater detail, searching for those crucial chemical signatures of potential biological activity. By doing so, the ELT could play a crucial role in answering the age-old question of whether life exists elsewhere in the universe, giving us not just a hint, but perhaps a direct glimpse of another living world. The ELT is also expected to make significant contributions to our understanding of the universe's earliest galaxies, providing invaluable insights into their formation and evolution, complementing the JWST's observations, but with different wavelengths of light. It will explore the nature of dark matter and dark energy, those enigmatic components that together comprise most of the universe's mass and energy content, but remain poorly understood. The telescope's observations will help refine models of cosmic expansion and structure formation, giving us a clear picture of the universe's grand design. Additionally, the ELT will study the properties of black holes and neutron stars, offering crucial clues about the extremes of physics where the laws of relativity and quantum mechanics intersect, probing the very limits of matter and gravity. The detailed observations made possible by the ELT will also allow astronomers to better understand the life cycles of stars from their birth in dense gas clouds to their explosive deaths as supernovae. By pushing the boundaries of observational astronomy, the extremely large telescope promises to uncover new astronomical phenomena and provide unprecedented insights into the fundamental nature of our universe, potentially leading to new physics and a deeper comprehension of cosmological and astrophysical processes. It's a silent, powerful gaze into the unknown, promising to transform our quiet contemplation into profound understanding. Now let us turn our attention back to our closest planetary neighbor, the red planet Mars. Even with all the incredible discoveries already made, upcoming missions to Mars are on the cusp of potentially transformative revelations aimed at unraveling the red planet's deepest mysteries and furthering our understanding of whether life once existed there or might even persist today. Imagine our intrepid robotic explorers diligently scratching at the surface and listening to the faint whispers from beneath the dusty red soil. One of the most anticipated areas of study involves the meticulous search for signs of ancient microbial life. Mars's ancient rivers, lakes, and possibly even vast oceans suggest it once hosted habitable environments, perhaps teeming with simple life. Finding fossilized microbial forms or clear chemical biosignatures of past microbial life in ancient sedimentary rock could revolutionize our understanding of life in the universe, showing us that Earth was not necessarily unique in its early ability to foster life. The next generation of rovers, with their advanced drills and sophisticated onboard laboratories, are designed to do just this, to gently uncover the echoes of life from billions of years ago. Another surprising area of investigation focuses on Mars's subsurface water ice and potential liquid water reservoirs. Recent missions have hinted at the existence of saline liquid water under the surface, kept from freezing solid by its salt content. Probing these hidden reservoirs could not only prove crucial for future human exploration by providing a sustainable water supply for future astronauts, but might also reveal environments where extant life that exists today could survive shielded from the harsh surface radiation and extreme temperatures. It's a profound thought that beneath the quiet, desolate surface, hidden pockets of liquid might still harbor living whispers. Next-generation rovers and landers are also set to study the planet's climate and geology in greater detail than ever before, providing deeper insights into its past climate shifts and the profound reasons behind its drastic transformation from a warm, wet world billions of years ago to the cold, desert-like planet we see now. Such data could be crucial for understanding Earth's own future and the potential habitability of other planets that might experience similar environmental shifts. Moreover, upcoming Mars missions could uncover entirely unexpected phenomena, such as novel geological or chemical processes, or even entirely new types of minerals that challenge our current understanding of planetary chemistry. The search for methane signatures, which fluctuate seasonally and could imply either biological or geological activity, remains a tantalizing mystery that upcoming missions will continue to explore with more sensitive instruments capable of detecting even the faintest whiff of this enigmatic gas. In essence, upcoming Mars missions carry the promise of surprise and profound discovery, potentially altering our knowledge about Mars, the feasibility of human colonization, and the conditions conducive to life throughout the cosmos. They are a silent, persistent invitation to listen more closely to our red neighbor, for it may hold secrets that redefine our place in the universe. And as we peer closer at our planetary neighbors, let us now listen to the very fabric of space-time itself for its softest whispers. The next generation of gravitational wave detectors, building upon the groundbreaking work of facilities like LIGO and Virgo, is poised to revolutionize our understanding of the cosmos by opening new vistas into the universe's most cataclysmic and enigmatic events. Imagine our current detectors as ears that can hear a loud clap across a football field. The next generation will be like ears that can hear a pin drop across an entire continent. These advanced observatories will offer significantly improved sensitivity over their predecessors, allowing them to detect gravitational waves with greater precision and from farther away, thereby increasing the volume of the observable universe from which we can hear these cosmic echoes. One of the primary enhancements these next-generation detectors will bring is the ability to observe a broader range of cosmic phenomena. This includes not only the more frequent collisions of neutron stars and black holes, which we have already begun to hear, but also the more subtle signals from supernovas, the explosive deaths of massive stars, and perhaps most anticipated of all, they hold the promise of detecting the much sought-after signals from the early universe, just moments after the Big Bang, a period currently obscured from our view by the cosmic microwave background radiation, which is the earliest light we can see. By probing these primordial gravitational waves, scientists hope to uncover details about the universe's birth and its very first chaotic seconds, testing and refining our models of cosmic inflation and the fundamental forces at play during that unfathomable era. The improved detectors will also significantly enhance our understanding of the fundamental physics governing black holes and neutron stars. They will offer deeper insights into their formation evolution and internal composition, allowing us to probe matter under conditions of extreme density and gravity beyond anything that can be achieved in any laboratory on Earth. It's like having a window into the most extreme physics experiments imaginable playing out on a cosmic scale. Another significant impact will be on the burgeoning field of multi-messenger astronomy. As we learn the detection of gravitational waves combined with observations across the electromagnetic spectrum, like light X-rays, radio waves, and other cosmic messengers like neutrinos, offers a holistic approach to observing the universe. This will allow for a more complete understanding of events like neutron star mergers, revealing not just the bang, but the light, the gamma rays, and the afterglow, shedding light on the origins of heavy elements like gold and platinum, and even refining our measurements of the universe's expansion rate. The next generation of gravitational wave detectors will not only provide a richer catalog of gravitational events, but also refine our understanding of the fundamental laws of physics, offering new insights into the nature of space-time and matter. Their observations promise to solve long-standing cosmic mysteries and potentially uncover entirely new phenomena, deepening our comprehension of the universe in profound ways. They are a silent, powerful symphony in the making, waiting to play the universe's most hidden notes. As our cosmic journey gently approaches its end, let us now turn our final gaze to perhaps the most profound and hopeful quest of all, the search for Earth-like exoplanets. This is a cornerstone of contemporary astrophysics, driven by the profound and ancient question of whether we are alone in the universe. Imagine our Earth, a fragile blue marble teeming with life, and then the quiet hope that somewhere out there another such marble exists, carrying its own vibrant story. This quest not only aims to identify planets similar in size and composition to Earth, but crucially also those that orbit within their star's habitable zone, that optimal distance where liquid water could exist on a planet's surface, a key ingredient for life as we know it. The significance of finding Earth-like exoplanets extends far beyond just the immediate quest for life. These discoveries can provide invaluable insights into the formation and dynamics of our own solar system. By allowing us to compare it with countless other star systems, it's like studying a single beautiful flower and then suddenly seeing a whole garden revealing the countless variations and pathways a flower can take. Furthermore, understanding the precise conditions that make a planet habitable contributes to our broader knowledge of planetary atmospheres, climates, and geological activities across the cosmos. As the search progresses, leveraging continuous advancements in telescope technology and detection methods, we may stumble upon truly unexpected types of planets that challenge our current understanding of planetary science. Imagine our current models being quietly rewritten by the universe itself. For instance, we might find Hycean worlds, planets larger than Earth, with vast, deep oceans beneath incredibly thick hydrogen-rich atmospheres. These worlds could potentially harbor microbial life in their oceanic depths, even without a conventional surface. Another possibility is the discovery of rogue planets with subsurface oceans kept warm by radioactive decay or tidal forces from their moons, proving that even worlds adrift in interstellar space could harbor liquid water and potentially life. We might also encounter planets in extreme environments that, according to current models, shouldn't support Earth-like conditions, yet somehow do. This includes planets orbiting within the habitable zones of red dwarf stars, which are known for their powerful stellar flares. Such discoveries could redefine our criteria for habitability, suggesting that life might find a foothold in places we once deemed impossible, a profound testament to life's resilience and adaptability. Each discovery in this search not only broadens our understanding of the universe's diversity, but also brings us closer to answering age-old questions about our place within it, highlighting the interconnectedness of cosmic biological and planetary sciences. It's a gentle, persistent whisper that we are part of a much larger living story. Finally, as we come to the very end of our quiet journey, let us contemplate the biggest, most enduring mysteries that still cloak our universe and the promise of breakthroughs yet to come. These are the enigmatic components known as dark matter and dark energy, fundamental to our understanding of the universe. Yet, they remain shrouded in profound mystery. Dark matter is thought to make up about 27% of the universe, essential for explaining the gravitational forces that hold galaxies together. Dark energy, comprising approximately 68%, is driving the accelerated expansion of the universe. Imagine a vast cosmic stage where 95% of the actors are invisible, yet they dictate the entire play. Potential breakthroughs in the study of these phenomena could dramatically transform our understanding of the cosmos, unveiling entirely new physics and reshaping our comprehension of the universe's fundamental structure and its ultimate evolution. One potential breakthrough could come from directly detecting dark matter particles. Despite its powerful gravitational presence, dark matter does not emit, absorb, or reflect light, making it incredibly difficult to detect with our current instruments. The discovery of a specific dark matter particle, such as a weakly interacting massive particle WIMP, or an axion, through sophisticated collider experiments, incredibly sensitive underground detectors, or dedicated astronomical observations, would open a new era of cosmology. It would allow us to understand the precise properties of dark matter and finally confirm its role in cosmic structure formation. It's like finally finding the missing pieces of a grand cosmic puzzle. Another significant breakthrough could result from uncovering the true nature of dark energy. If scientists are able to determine whether dark energy is a constant, as in Einstein's cosmological constant lambda, or if its strength varies with time, it could answer fundamental questions about the very fate of the universe. Experiments designed to measure the expansion rate of the universe with unprecedented precision, or to map the large-scale structure of the universe in exquisite detail, could provide the crucial insights into dark energy's characteristics. Is it a static property of space, or a dynamic field evolving with the cosmos? Moreover, the dream of discovering a unified theory that encompasses both dark matter and dark energy, perhaps within the framework of quantum gravity or string theory, would represent a truly monumental leap in physics. Such a theory would not only explain the nature of these dark components, but also offer a more comprehensive understanding of the fundamental forces and particles that compose the universe, bringing us closer to a theory of everything. Unexpected findings, such as the discovery of entirely new particles or forces that do not fit within our current standard model of particle physics, could also emerge from the study of dark matter and dark energy. These discoveries could lead to the development of entirely new physics theories that bridge the gap between the whimsical quantum mechanics of the microscopic world and the grand general relativity of the cosmos. Breakthroughs in understanding dark matter and dark energy have the profound potential to unravel the deepest mysteries of the universe's formation, structure dynamics, and ultimate destiny, marking a true paradigm shift in our cosmic perspective. As we gently close our eyes and let the quiet whispers of the universe settle in our minds, remember that the cosmos is a place of endless surprise, of beauty in its complexity, and of profound mysteries that invite us to simply wonder. We are but tiny observers on a small blue planet, but our curiosity reaches across billions of light years, listening to the echoes of creation and the promises of discovery. The journey of understanding the universe is never ending, a silent, beautiful lullaby of inquiry that continues into the vast, waiting darkness. Sleep well, curious mind, and may your dreams be filled with cosmic wonders.